So,
Ulrich?
Right. I also heard the church bell ring. It's 3 in the afternoon in Europe, and whatever it is in your time, early in the morning or middle of the night, and
8 p.m.
8 p.m. Yeah, you're welcome. And so I think we have an exciting schedule today with got lots of good programs, talks. Here is the schedule, and yeah, welcome everyone. And I think without further ado, I would ask Adrian McMenamin. Yeah, you will tell us how to pronounce this.
No, you got it right the second time.
The second time, okay. And I'm very excited to hear about RiscV Forth. So I stop sharing my screen, and you can do it. And then you just go ahead. And I'm happy that we meet again.
Okay, sir. Okay, sir. And if any problem, I talk with Peter, sir, and I think he helped me a lot, sir. Okay,
Yes,
sir.
but you need to reserve a piece of your cake. I will ask a piece of your cake.
Okay, sir.
Okay, shall I start then? Are people ready? If I can get this.
Right, we see your screen. That's great. And
okay,
yeah, please go ahead. The stage is yours.
Okay. I'm just going to start with a very brief presentation. It's just the 5 slides, including this title slide, just to explain what the motivation was and what some of the issues are. I mean, I take personally, I take great pleasure from what I've done, and I'm proud of it. But I'm not going to make any claims that this is an earth-shattering project. It is to develop a Forth for single board computers using RiscV. Started more or less about a year ago, because at the time it looked as though we were going to get a flood of single board RiscV computers onto the market. There was a big fuss in January last year about Beagle 5, which is going to be the first low-cost, mass-produced RiscV SBC. Unfortunately, although prototypes were made for that and they were sent out to be tested, that project has been cancelled, though there is hope that we're going to see other RiscV SBCs in the year ahead. There is actually one on the market now, the Nesha board, which I do have. It's not really, it's not particularly low cost. It's about $100 US dollars, I think. And it's not been huge numbers made, but it does work. It's got a 1 gigahertz single core processor on it, and it's what I actually now do most of my development on. But you can also use QEMU, and originally I started off by using the Spike emulator. So why did I do it? Well, for fun mostly for my own fun, and then hopefully to be able to give some pleasure to other people who were using these RiscV SBCs. I mean, my immediate motivation was that I thought that with these coming onto the market, and when you look at the ecology around the Raspberry Pi, it would be good to have something which allowed people getting these RiscV SBCs to get some easy access to the hardware and do stuff with hardware without necessarily having to deal with all the boilerplate that comes with other languages. And Forth seemed like a good option, partly also because, I mean, I admit I'm a child of the 80s in computer terms. And when I first started using basic computers, microcomputers in 1981-82, Forth was always held up then as the sort of faster alternative to basic. So it's always held a fascination for me, although I hadn't actually really done anything with it. So I thought it would be a good thing to go and develop my own. I also had this naive belief that nobody else would actually have made a Forth for RiscV processors, when actually, you can see that there are quite a lot of different varieties out there. So how's the project evolved? Well, I originally started Christmas time last year with the view that it was only going to last a few weeks, partly because the book that I had, which you could get online, about threaded interpretive languages, says it only takes a few weeks to develop a Forth for Z80 processor. So I thought that would be pretty simple. It's obviously been now going for a year. I started off with the idea that I'd write a threaded interpretive language, which would be similar to Forth, but I wouldn't really necessarily stick to the standard. The longer I've gone on, it became more Forth-like, and now actually my view is what I'm really trying to do is match something which meets the Forth standard. And I do actually now meet most of the 2012 core standard. So there's been quite a lot of progress on that. It's all, I mean, one of the interesting things about the standard versus the hardware I'm using is the standard's obviously written on the basis that cells are 32 bits wide, while the hardware is 64 bits wide. So, I mean, I'm really using stuff which is everything is 64 bits wide. And as I said, it runs on the Nesha single board computer, and it will also run on QEMU. There are some pretty serious limitations with it at the moment. It doesn't have any floating point support. It doesn't really have any graphical or even sort of sophisticated text output. It's just basically it is very 1981 style lines of text output. There aren't really any other users. I mean, maybe that's because there isn't really any other hardware out there. When I say there's no hardware support, what I mean is, although my original motivation was to write something which would allow people to hack the hardware, I haven't really written any sort of specific hardware support code. I mean, I've really concentrated on the core language itself. And that's because there isn't really a big community out there at this moment in time. So it's seemed more opportune to get on with building up the support for the language, the core language, rather than looking at the hardware. And in terms of what will come next, I mean, I could actually adding the floating points support and curses, end curses type support isn't that particularly difficult. It's really a question of finding the time. There is OpenBSD, which runs on QEMU, and it would be quite good to port to that. I don't think that's going to be that would be that challenging a thing, just making sure that the library commands all match. And it would be good at some point to get this packaged for Linux distributions, which are for RiscV. And it would obviously be great to get more users, contributors to the project. So that's the sort of the background to it. And if I can work out how to do this, I will now actually show you it running. Okay, just bear with me a second. To share another screen. So hopefully you can all see a blank terminal screen. Nobody's saying anything, so I'm taking that as a yes.
Yes.
Okay, right, so if I just run it, I mean, it's a pretty crude interface here, but I mean, it does the basic things that you would need. There is an issue about some of these the words. They aren't defined in the way that you would expect. Just there might be in the full text form. That's to do with, I mean, that's a sort of technical debt, which I still haven't dealt with in terms of how the assembly works for these. I mean, basically, I have an issue with assembly macros and equal signs. So GTEQ is actually greater or equal to greater than or equal to, and you can actually write that out as that in the code, but when it comes up as a listed word, it comes up on that form. And I think the thing to do is just show you the tests that, so you can sort of see, this gives you an idea of the words that are supported. It's nothing particularly exciting. And that's it, basically. So that's a quick run through of it, and this is just some of the code, just so you can see what it looks like. And it is all written in RiscV assembly. In terms of performance, just one additional sort of thought. And some things, I mean, I've essentially measured it, not in a particularly sophisticated way, but measured some of the timing performance against G4th, and some things it does. I mean, it's about 10% faster than G4th. Other things, I've basically noticed that the create, my create seems to be probably a bit slow. So I think I need to work further on optimization of that, because when I've run a proper matrix multiplication benchmark code, it is about, my code's about 10% slower than G4th. So, and I think just from some crude profiling that I've done, I think that's to do with the way the create code works. And I've got some thoughts about how to deal with that. But I mean, in general, it runs at a reasonable speed. But it's not, I make no claims that it's particularly super fast just because it's written in assembly. So that's my sort of run through of it. And if anybody has any questions, I'd be more than happy to answer them.
Yeah, right. Thank you very much. And are there any questions?
Yes, Christian has a question.
Go ahead.
My question is there any RISC feature that makes it better for Forth? You wrote something, you wrote Forth with it. You must know all the features that help you.
Well, I haven't written a Forth for any other language, any other sort of processor. So in one sense, I don't have a comparison to draw there. I don't. I mean, the idea behind RiscV is to have an open and clear instruction set at the assembly level, rather than, if you look at the x86 family, they've essentially been, I believe, if you average out over the last 40 years, one new instruction has been added per day, essentially, over the last 40 years in that family of processors, and that is not proposed here. At some point in the future, RiscV will quite likely to have a vector instruction set, which could be quite useful. It's not in any of the cores I'm using, so I don't get any particular advantage out of that. I mean, it was written I decided to go down this way, writing one for RiscV on the basis that I thought that we were going to get quite a lot of low-cost RiscV single board computers on the market this year, and that hasn't happened.
So RiscV was chosen mostly because it's a free instruction set.
Yes, I mean I had essentially just completed a PhD, and I'd used RiscV in that, so I had a bit of familiarity with the instruction set, and I thought it was, you know, there's no shortage of, at least this was my view, there is no shortage of language support and coding ideas and similar things for ARM and for Raspberry Pi users. So I thought, well, there might be some new users of RiscV single board computers. Let's produce something which will be useful and helpful to them.
I heard you mention vector instruction. Could you explain what it is?
Well, the idea, so that is the idea that you essentially apply a single instruction across a large number of memory locations or registers, all in parallel, all at once, so that you can essentially you can get a lot faster arithmetic. So it's quite useful for sort of heavy computational arithmetic tasks, possibly graphical processing tasks, those sorts of things. I mean, essentially, I mean, I'm not speaking from experience here, but rather from my understanding. But, you know, if you think of a sort of a supercomputer, a very parallel supercomputer, it is set up to do this, you know, the same calculation in parallel millions of times, and very quickly. Having a vector instruction set allows you to replicate a little bit of that in a single processor.
Thank you for taking the time to explain.
That's no problem.
You satisfy my curiosity for today.
Okay, thank you.
Great. So Dimitri, you raise your hand. And the mic.
Yes, I think I'm on. Okay. Yeah, I might not ask the question completely correctly, but I've always wondered this because I've been into RiscV for a few years, and one of the things I always thought of is you have, I think, 31 registers normally that are available. And what would happen with a language like C is it kind of uses them like a stack. It's not a real stack, but it's almost as if it's a stack when it's evaluating the expressions. But I thought, well, that's a very difficult thing though to do in a Forth implementation. So I wondered how registers of RiscV would be used when implementing a Forth on RiscV. So my question then is, how many of the registers did you use?
Okay, I'm just going to quickly consult my book here just to make sure I can get the count numbers right. So just bear with me a second.
Could be used exact as a PDP.
Sorry.
You need at least 6 registers.
Well, I mean, in the way that the registers are structured, I mean, obviously, in theory, you could use any register for whatever you liked, but this is the standard way that they are used. Is you have 7 temporary registers, so they can be used for anything you like, and I just tend to use those for sort of general computational stuff. You have 8 registers which are used for function arguments, and certainly if you're passing anything to the C library, you need to sort of set those up. But they are inside your own code. You can essentially use those in any way you see fit. And then there are a further 12 saved registers, which the values of which are meant to be preserved from one function call to another. Now, what I actually do with that in Forth is that I do cheat a little bit with those, because I know then that if I put store values in those registers, when I call into the C library, they won't be, the values there will not be changed. So they are quite useful for using as stack registers inside Forth, because you know that they will be preserved from call to call. So I don't use, I'm only using 3 of them, but they are, that I do use them as things which will be immutable as you sort of pass back and forth to the C library. So that's how I use that. You can also, I mean, in some 1 or 2 places, I push a lot of registers to this to the stack, so that you can then use more registers as well, in the same way that, you know, would be familiar to anybody who's you know, written functions in assembly before, so that you can just sort of stick everything on the stack, do what you like with the registers, and then just pull them all off the stack at the you know, before you return. So there's 1 or 2 places I do that, but in general, temporary registers just used for routine calculations. The function registers used occasionally for routine calculations, and sometimes to call into the C library. Save registers generally don't touch, except that those ones which I use to ensure that I've got immutable stack pointers, which will be preserved as I call in and out of the C library.
Okay, that's really interesting. So you've actually used the RiscV ABI when designing this. Okay, that is really interesting, and how you've used the save registers for the stack pointers, but you were following the ABI. Okay, thank you. That answers my question.
Okay. Right. Any additional questions to Adrian? Okay. Yeah. Well, then I take the pleasure to take the Christmas hat and to give a talk on arrays again. Some tutorial, and let me see, I share my desktop, and let's see where we are. Here we go. You should see my slides, is that right?
Yes.
Okay, fine. So I would like today talk about arrays again, and especially the automatic resizing issue, and then some thoughts on RAM-ROM distinction. So let's see, this is the overview. I talked about data structures in the last meetings, in the tutorial part as well. And so the idea is to explain how you add the missing features, the missing features in Forth. And we will look into that shortly again, and recapitulate how we define arrays in Forth, and how we do this with implicitly within defining words, and look at the simple arrays. Then I will talk about the bounds checking, and today's main topic would be the automatic resizing of Forth arrays, and hope we come close to that. And after that, I'm talking about a little bit about RAM-ROM and how you can strive to make portable programs that work on RAM-only systems or on RAM-ROM systems. So, yeah. So as a newcomer, you often hear or you recognize that Forth does not have a certain feature, X. So, and then you go ahead and ask, well, it doesn't have a case statement. You can use, you can define it on your own. Well, it doesn't have structures, or it doesn't have arrays. Well, you can define arrays on your own. Yeah, depending on the application you choose, whatever is suitable. And the question really is, how do you do that? And that's the main topic of this tutorial section. So we look at these kinds of things, and The key feature is that you have to organize the memory in Forth yourself. What you get is exposed memory with addresses and read and write operators, which we call fetch and store. And so let's see, and this is what it looks like. You can allocate some memory and you do this normally within the dictionary by means of the lot operator. And if you have a defining word, then you can use it to define new words, and that have array-like behavior. So you reserve memory for it, and then you define the behavior of the word. And what should an array word do? It should take an index, and it should return an address of the appropriate element within the array. And the way that create does works is that the start address, the parameter field address of the defined word is put on the stack. So actually when the does part starts, you have two elements on the stack, which is the well, that's just the other way around. So the index is at next of stack, and the address is on top of stack. That's the reason why we have the swap here, so that we can do the appropriate address calculation, multiply the index by the size of the elements that you want to address, and then add up the base index, the base address of that thing. So SQ is actually on top when you start executing this, which means if you define an array like this, array will execute the create part, create the memory data structure here, and then define the word SQ that has the parameter field here, and has the behavior to do the appropriate address calculation. So after that, you could probably, you can go ahead and store some parts. If you have the address of an element, you can store data in it. So you can say 16 for SQ store. SQ is an array, does the appropriate address calculation from its base address. Given the index, it calculates the address of the fourth element and gives you the address, so store can store the value 16 in there. So, and that's, if you don't need more, then you can go ahead, use this to do this. Even you can do address calculation on your own if your program doesn't want to use defining words or whatever, but we start from there here. So let's see. You can use the same interface, like define an array with a defining word, and then do also index checks. So if you use an index that is out of the area that you have been allocated for the array, then it might be nice if you get an error message or an exception is raised, so that you can handle it in your program. And so we go ahead and define the array slightly in a different way. Now it has also some area where we store the size of the array. Yeah. So in the case of 6 array SQ, we store the size, and then we allocate the appropriate elements, or space for the appropriate elements. And the behavior now goes ahead and checks, fetches the length and checks whether you have a valid index. And if not, it throws, well, standard throw codes. It throws an error, invalid numeric argument. So you know, then if you use that, then of course in cell 4 you can still write the appropriate value, 16. But if you try to access element 6, then you get invalid numeric argument, as it's out of bounds of where you are. Right, so that's one thing. And the typical way that we use to represent the arrays here is that we use the parameter field of the new defined word to store the data for all this the elements and also the size. Yeah, but there's also the possibility to do it in a different way. So we did it like this, and we had this source code here. But we can also do it in a different way so that we do an indirection. So within the parameter field of the new defined word SQ in our case, we have a pointer, the address where the actual data starts. Yeah, and this has the advantage that we can change the address to some other area and update the pointer. So this could make a good place for additional features. And so then array changes a little bit because we need to allocate the appropriate memory, get hold of the address and store it in the parameter field of the new defined word, which means here we go ahead, take the number of cells that we want to allocate, we do the appropriate allocation, and this phrase actually leaves the address of the new memory on top, and then we store it in the appropriate thing. I'm used to use here where I say, okay, this is what has been allocated. The length is stored, and then the number of elements is allocated, and we get the address on top of the stack. And now we create the words and comma the appropriate thing, which creates the parameter field and stores the appropriate address here and the pointer in there. The behavior is nearly identical to what we have above, where we started with the index and the parameter field address, did the appropriate index check, and then did the appropriate calculation to with cell plus to get to the first element, and then do the appropriate address calculation. And here we do nearly the same, but because of the indirection, we need to fetch the address to get to the appropriate allocated data. Right. So that's one thing that we can do. We can split the place where we store the data from the word and have it allocated at some place. And this opens the possibility to resize our arrays. And if we look at the support for dynamic memory in Forth, then we have mainly three words, which is allocate, takes a number of bytes that you want to allocate and reserves that number of bytes in memory. How it does it, if it asks any operating system, or if it manages this on your own, that's open. What you know is you get an address and some success indicator, 0 if everything is successful, or some throw code if something went wrong. And then there is free, where you can say, I no longer need memory. This can be reclaimed and can be used for later on. And if I free something, I get also a success indicator. And the third function, that third word that is especially interesting for us here is resize, which takes a memory address that have been allocated and a new size that we want to have. And it makes sure that the reserved memory either shrinks or grows, and returns the address where the data now is, and also a success indicator. So this grows or shrinks, and it might be that the memory management is not able to allocate to just resize in place. So it needs to allocate a new larger block, and then all the content of the existing memory needs to be copied over, and resize guarantees that this is the case. So it preserves the content of the resized block. Although it might not stay at the same address, the content will be the same before resize is called and afterwards. But maybe it allocates a larger block if necessary, copies over the old data, and gives you the new address and a success indicator whether this all have been worked out fine or not. So that's the fourth way. We have dynamic memory, similar to C alloc function calls. And with this, we can go ahead and do a very similar thing. So we still create the same data structure as with the resizing, with the bounds checking array. But instead of throwing an error in every with every index that is out of bounds, we only throw an error if the index is below 0, because then it's obviously somewhere where we don't want to address memory. But if it's large, then we extend the array appropriately, so the index will actually fit in the memory. And then we have a larger array and we can store the appropriate values. So, and we do this by invoking this fit word here. And fit makes sure it gets the index and the array address on the array address here on the stack, and makes sure that the index fits inside the array, increasing the array until this fits, and that you could have different strategies to do that. And one very clever strategy is to double the size of the array until it fits. And then normally you have something that is good enough for many other indices that you might want to use to store things. So again, we define an array, now a resizing array called SQ. It has the same interface. So you give it an index and it returns an address and you can store values there. So 16 for SQ still works, nothing happens. We do this underflow check. It's not triggered, and fit will just say, well, 4 is good enough for our array. We can return the address and store can actually put the value in there. But if we access element 31, then that's actually not inside the valid array that we currently have, because it's only 6 elements large. So fit will increase the array. We'll see, oh, 12 is not sufficient. We'll increase it again. 24 is not sufficient. Increase it again. 48, yeah, that's fine. 31 fits within 48. And so increase or double the size of the array 3 times, and then returns an appropriate address, preserving the content that the array already has. And then you can store 961, the square of 31, in that. Yeah, so let's see how fit will work. It will actually try to compare that everything's that the index matches the size of the array, and if not, it will invoke double, and double will go ahead and call the appropriate resize. Yeah, and resize, so it doubles here 2 times. It doubles the size that we have. If the resize is successful, then it stores the new length at the beginning of that block. And so you can call double again. So if you access the array with 31, 6 is not enough, 12, 24, 48 is what we get. And the memory is enlarged so that we have 31, where we can store 961 later on, and it goes up to 47 because the size is 48. So that's rather nice. And let's see, I think that's a good place to have a look at the demo. So here is again the source code that I just presented, with the addition that I'm outputting something when we invoke double. And so we defined our array SQ. With that, we stored 4 in there, so we can say 4 SQ fetch dot. Yeah, not surprising, there's 16 in there. And now let's see, we can say 961 31 SQ, and I'm not doing the store right now because we want to inspect what's on the stack afterwards. And we say this, and it says double, double, double. And so let's see what's on the stack. It's an address and the 961 that we had, and I can say store here. So let's see, what is the size of the array that we have? So we tick SQ, go to its parameter field, fetch the address of the memory area that we manage, and then we fetch the size of the allocated block, and ta-da, it's 48. Great. So that works fine. And so what we have here is the parameter field has a pointer to some data, and we can change that data very easily to contain different things. We can change its size if it's managed data. And this made me think of, well, maybe this has something to do with RAM and ROM, and a very similar structure that we have is if we look at RAM-ROM systems. So if you look at Forth systems, there are, with the idea of using flash or ROM or RAM, there are two flavors mainly. It's the RAM-only systems, those systems that just have a single dictionary and manage all the operators in this, all the memory in the same way. All words operate on RAM. So if you allot something, or if you allocate something, if you comma or whatever, then it's all in the same memory area. There's here that points to the free available space and so on. And then there are RAM-ROM systems that also have flash. It could be that you just have program storage in ROM, but it could also be that you want to have some data there. And this is my concern here. So a good distinction, some Forth systems do it, is that they say allot and here actually work on RAM part of the memory, and comma and C comma, where you want to build up tables, for example, they work on ROM. And then the question is, can you write definitions that will work on RAM-ROM systems, although you don't know actually how they do it, assuming that they use allot and here for RAM and comma and C comma for ROM. My claim is if you want portability on RAM-ROM systems and RAM-only systems, you assume that you have a RAM-ROM system and include the indirection that we've seen, then the definitions will run on both systems. So a typical word that shows, or a simple word that shows this behavior is the word buffer colon, which allocates a buffer, very similar to what we have with an array, only that it doesn't do the address calculation on its own, but it just returns the base address of the allocated memory. So a most simple form is create allot. And there's a lot of debate why you would have buffer colon if you could just write create allot. And here is my take on that. So you can use it in RAM-ROM system as well. Then if you have an indirection, buffer colon will actually, in its parameter field, will have a pointer, the address of the buffer, which might not be changeable because it's in ROM, but it points to a RAM area that you can use for storing the data in the buffer, which is a pattern that is very similar to what we have with the indirect array. So we do here swap allot, leaves us the address in RAM on the stack and allocates the amount of U bytes. I use these kinds of structure pictures to describe how the memory is organized and how it's separated. And then we do create comma and store the pointer to RAM in the parameter field, and assuming code and the parameter fields of words go in flash or ROM, you can't change it later on, but it points to appropriate region in memory. And now you need to do the indirection. Here create will just return the address of the parameter field. And here you need to actually fetch the pointer to get the address of the RAM. Yeah. And so if you look at this, both definitions will work on a RAM-only system. Only this one looks strange because it has this indirection that you don't know why it is, but now you know. The bottom definition actually works in ROM systems as well. Yeah, that follow this convention. So I started to do defining words when I know there is also the chance that this need to run on a RAM-ROM system. I started to define words like this. Yeah, maybe I start with the bottom, with the top one, and then I said, well, I have a good pattern of how to move to the other way. Okay, so that's what I wanted to talk about today. So automatically resizing forth array, making use of forth built-in memory management. So if you don't have resize, allocate, and free in your system, then that's probably something that you need to add if your application requires this kind of features. Yeah, I talked a little bit of RAM-only and RAM-ROM systems and how to write definitions that are likely to work on both systems. If we look at the whole sequence of things that we looked at, we can make another check mark on automatic resizing and RAM-ROM systems. So we talked about structs, arrays, and now the resizing things and enumeration types last time, which leaves us open with objects, something that is a great topic for 2022. Thank you very much for listening, and I'm open for any questions.
Wonderful, Ulrich. Excellent.
Okay. Yeah. Other questions?
Guess what? I have a question.
Sure. Yeah.
You covered most of the data structures, but the question I have now is, which one is good for what?
I see. Yeah. So
frequently, I don't know what to choose.
Yeah. So it's mainly if you have names for different parts of your the data that you want to store. A struct is probably the fine thing. You give names for certain parts, and if you just have a sequence of things, then an array is appropriate. And you could, of course, you could nest this. So if you have some records and you want to have an array of records, then the appropriate size of the things that you store in there is different, and you have to do the address calculation a little bit different. Yeah, but that's mainly what it is. So if it repeats, then an array is the appropriate thing, and if it's different parts that are also of different quality that belong together, then a struct is the appropriate thing. Yeah, and then in doubt, think about one or the other and ask yourself the question: do I need more of them? And then an array is probably good. Does this have some kind of structure? Is it primitive, or is it composed of different things? And then a record might be the right thing. Yeah, and then you try out.
I didn't get exactly the difference between structure and enum.
Enum is just a name for different values. So it's not a you name in principle atomic values like states in the state machine or colors or weekdays, and there's no further structure involved there. You just give names to distinct values, and yeah, that's what an enum is for. So you don't need to write magic numbers in your source code, but you can just use the names.
I have a question, but maybe it's not such a question. When I saw 6 and SQ, and then you go enter to see the result.
Yeah.
I thought that it's the same that you had a word that calculates the square of the number. So this array that extends itself should be seen like a memoization. So you can pre-calculate some many values. Is the same, or it's feasible?
Yeah, that's of course that's possible. Yeah, you could either think of calculating things up front when you load things, then so that you build up the table, or it could memorize this. And yeah, of course, the running example is just a table of square roots, and you need to fill it. Yeah.
You're right.
Yeah, but of course, memorizing that array would also be fine. Maybe you have to supply the formula to calculate the values as well. But yeah.
Every time I listen to you, Ulrich, you give me very good idea.
Okay, and thank you.
It's the third time, I think.
Yeah, thank you very much. Yeah, I encourage everyone to experiment with this. So go ahead and try things out. Yeah, as you see, the simple interface, you have a word that takes an index and returns an address that you can later work on, can have lots of magic inside. So like resizing and checking the index, or resizing the array appropriately to satisfy what the user need is. Yeah. Of course, if you have a program that runs nuts and says 1,000,000 SQ, then it would extend this a lot. Let's see what the forth system actually does here. I'm curious now. Let's see. So if I have 1,000,000, well, that's 1,000,000 SQ. Yep. Well, this does it. So very nice. And let's see what SQ actually, what size it actually has. 1,500,864 elements. Yeah. So, but of course, I probably can kill it. No. Well, this is the issue with these modern computers. They have so much memory. Yeah. Anyway. Are there any other questions? So Dimitri,
I have a question.
Yeah, okay. Please.
So, well, one question and one comment. So normally in Forth, right? Because when I was learning, I kind of learned that the simplest array is use create and then you allot how much memory you need. Are you saying that and you can't necessarily comment on all Forth systems, but if you try to access something outside of the memory you allotted, would the Forth system normally allow it, or wouldn't you have an out of bounds thing?
No. The normal thing, if you use the first definition that I gave, which just does the address calculation, you just access memory outside this. If you fetch, well, then normally this doesn't have a negative effect. If you store their values there, then you overwrite something, probably, yeah, depending on the Forth system, other data or even code, or well, maybe worse, the link address of some word, and then your dictionary is corrupted. The next time you do words, the system will crash. Or so that's yeah. I think my main statement is you do whatever is appropriate for your application. So if during development you need bounds checking, then you use the bounds checking version of the array. It has the same interface as the normal one. And then either you omit this or you keep it in the application code. But if you're confident that all array accesses are fine, then you can just use the simple one. And if you don't know upfront how large the array indexes are, then the resizing array might be appropriate. Maybe you put in some upper limit, so that if you say 100 million is the index, it will still throw some, that's out of bounds. We don't want to support that. But it would just resize appropriately. And so if your application need is like that, then go for it.
I see. You have both answered my question and gave my comment, because I was going to comment and say exactly what you said, which is, yeah, you implement what you need. And I actually quite like this about Forth, although it was strange at first. Why don't you have all these things built in? But you can design them to suit your application. And I found many cases you don't need the overhead that normally comes with, say, structs and arrays. You just need things that are stored in next to each other, or things that, I don't know, they're stored in a pattern that you can remember, or you have words to access. So yeah, I agree with that. That's it from me.
Yeah, actually, so that's the idea of the project FORTHworks, where we collect ideas. So you need to, of course, you need to have your tool set. You need to know what to do to achieve a certain effect, and that's what the project FORTHworks is about. Collect these ideas and write down so that you can go there, consult the idea, and say, well, this is what I need for the application right now, so I can incorporate this and define the structures and the words that are necessary to support what I need. Right. Any other questions?
Ulrich, it's better we move on with the next.
Sure.
With Matteo Vitturi from Italy. He is going to present a Z80 Forth for the Spectrum computer.
Great. I'm looking forward.
Thank you, Ulrich.
Sure. You're welcome.
We cannot hear you, Matteo. Your microphone is off. Your microphone.
I think you're on mute, Matteo.
Perfect.
Yeah. Can you hear me now?
Yes, yes.
No. Yes? Okay.
Yes.
Looks fine.
Sorry, I couldn't find the control. Well, I hope you can see my share. Well,
Yes.
okay. This what you see now is the emulator of the ZS Spectrum Next. So I use directly Forth to show Forth, okay? Because Forth in my life is, I use just to play games and not for professional use. So let's start. I started when I bought my first computer. Then in the 90s, I disassembly white lighting Forth. Then I tried to implement the ZX micro drive. So I just recompile everything to work with the micro drive. Do you know why micro drive? I think you know that is the worst mass storage unit available in the market. But this is what I got in the 90s. Then I had to, because the Spectrum is very fragile, I had to put aside everything. But I found emulators that works with micro drive, and so I restarted this Forth. This is my passion because I don't use Forth for professional. I use other language, but I have to breathe some Forth every so. I continuously improve this Forth for my pleasure, and then in 2021 I found Albert van der Horst's work. It is an 8080 Intel assembler and disassembler altogether, but what I need was a Z80 assembler. So I simply filled the gaps between 8080 and Z80 to obtain an assembler. This is a people say that this is a very nice piece of software I ported. I did not write it from scratch. I simply improved Albert's work to do his job. And so I also ported to disciple version. Then when I got my Z Spectrum Next, I could port on a total new computer. So inside the SD card of the Spectrum, I structured things like that just to know. The memory map, okay, let me say a few things. The new Spectrum Next comes with a huge amount of RAM that you can split, you can fit in 8K page. So reading from the bottom, I use the last 8K page to fit all the RAM available. Then I had to scrunch everything to fit the Forth itself to work with the Spectrum, because I didn't want to lose the feature of the Spectrum itself. So let me continue. In the years, I developed some utilities, for example, an full screen editor for blocks and screens. And then I developed the C and the assembler. Then when I had so much memory available, I also invented some heap utility. I also, I also implemented some interrupt routine and to see how it works. The floating point option is available, but is the ZX Spectrum original one. I simply use the ROM routine available. And then I found also some standard tests to prove that this Forth is quite standard. Well, let me see something. I already did some loading beforehand, so we can show what. Okay, I'm just showing you a few seconds of game. This is written in Forth. Simply. Okay, just to say, sorry. Okay, and for example, I had another thing that was to show color picker. This is sorry, the wrong palette. I had to reboot everything. I'm sorry. I'm sorry. This is the live problem. Okay. Sorry. Okay, let me explain a few minutes about the assembler, because it's very fun, very useful, how I can define words and opcodes and write in assembler that is quite very similar to the original Z80 syntax. So the push IF and a dash is a Forth definition. So for example, I had to define the family of the registers and the opcode, and then I can use them to code using a Forth assembler directly. And this is another example of how this assembler is coded. It's very similar, in my opinion, to the original syntax of Z80. So you can see that you can just remove some space and remove some comma, and it is exactly the right syntax. I had to, for example, I had to specify that the argument is number of address to be sure that the syntax is correct, but it's just what I follow in the Albert's work. Okay. For example, I code the dope duplication word exactly like that. It's, what you can see in this Forth that I use the index register IX to contain the next address of the inner interpreter. So this led me to a vectorized jump to the inner interpreter that allow me to implement a trace utility. For example, if you change the address of IX at runtime, you can change the behavior of this Forth. This is not my idea. I stole this idea from Marcos Cruz from Spain, I think. Anyway, this is jump IX is faster than just a simple jump, because JPIX is 8 t-state. Instead, a normal jump is 10 t-state. Okay. Then the last thing I want to say is that in the beginning, I code this Forth using an indirect threaded code. And this is what you see now is the inner interpreter. In the right was the old indirect version. In the left, you can see the new direct that spare some tick states. So everything is faster, but you have to spend some memory to do the jump. For example, the enter routine needs a call enter to perform everything, and I saw that the overall payoff is between 39% of faster, between and 9% faster. It depends on how the words are shared, because if every word, every definition is written in machine code, then you have the maximum gain of speed. Instead, if you have to enter like normal everything column definition does, you lose some speed performance, but it's not so bad. In average, I saw that the direct versus indirect, you gain something 25% of speed. Okay, that's all. Let me try to, I don't know how to stop my share. Help Peter.
So if you move up, there should be a green bar, and below that there should be something that says stop. But if you don't, yeah, no, that's
no. This is my desktop. Sorry.
But I can do it for you.
Let me. Sorry, I lose my control. Sorry.
Oh, that was not it. So I switched off your camera. So I'm sorry about that.
Sorry.
Like this. Here we go. Thank you very much. So please switch on your camera again, and maybe there are some comments and questions on your talk. Thank you very much.
Matteo.
I really enjoyed this as a Spectrum fan, of course, and I'm looking forward to play on it. Yeah, so that's
yes. Let me see. Can you see?
This is Christian. You just brought back memories. I had the ZX81 and used that assembler to write a little program to transfer my programs from an Apple II clone to the ZX81. So I had to use the assembler to do the programming in assembly to send it to the Apple II, and then I had to do the same thing in the assembly of the Apple II to send it to the ZX. I couldn't remember what it was like. Now I know. Thanks.
all right. Other questions, comments? So,
hi, Matteo. This is Rob. Thanks for the presentation. It was great. I haven't got my Spectrum Next yet from the Kickstarter 2, but I'll definitely be using the V-Forth when I get it. I've got my two of my children into programming as well. They're teenagers, so I'm going to start teaching them Forth using the ZX Spectrum next.
Ah, excellent. Right. So that was Z80 or Z80, however you call it in your dialect of English. And so thank you very much indeed. And we go to the other microprocessor, the 6502. And so our next speaker will be Alex Dumont. And he will talk about his forth called Alexforth, and it's for the 6502. So Alex, are you prepared to show your presentation?
Can you hear me okay?
Yeah, we can hear you.
Okay, let's share my screen now. Okay, that's not what I wanted to share. Okay, can you see the screen?
Yeah, we see
okay.
the screen. And
okay,
yeah,
try to remove.
Great.
This.
Please go ahead. Thank you.
Okay. Okay, so thank you. I'm Alex Dumont. I'm going to talk about how I implementing my own version of Forth on my 6502 breadboard computer. So this is more or less the overview of the presentation. First, I will give a small introduction of my motivation, some background, and I will present an overall of the 6502 breadboard computer I have built. Then I will give some 6502 basics, so we can understand for those of you who don't know the 6502 what this processor was and the constraints of this processor. Then I will try to give an understanding of how I implemented Forth on this computer, and then finally a quick demo. I'm afraid I may have too much content, so maybe I will have to skip some part at some point, but anyway. So to start, my motivation in this project is really to learn new things and enjoy. There is absolutely no professional ambition for this project, no financial or nothing related to money. So it's just to learn. And I discovered Forth in April this year, so it's really recent to me. And also I never wrote any assembly before this project really. So I'm sure if and I'm not a software engineer nor a computer science engineer, so bear with me if you see horrible things to your standards, because I'm really a beginner in the field. So here is my breadboard computer. For those of you who may know Ben Eater on YouTube, he made a series about building a 6502 breadboard computer. So that's what I follow to build this computer. And you may recognize all the components of the same architecture. I just added some component at the top. So basically the computer has a 65CO2S processor, which is the most modern version of the late 6502. This one is a CMOS version and a static one, which means that you can pause, you can slow down the clock, or you can even pause it and it will still retain the register value. Then the computer has a 16 kilobyte of SRAM and 32 kilobyte of ROM. And there's also a 6522 versatile interface adapter, which will give a 2 8-bit general purpose I/O ports on the bottom, and at the top there is a ACIA, which is a asynchronous communication interface adapter. So basically it's a serial port. That's how I will communicate with the computer using an FTDI USB dongle. As you can see, there is no keyboard nor any VGA display, but there is a 20x4 LCD display at the bottom. At the time, I also built an EEPROM programmer, but right now it doesn't work anymore, so I'm using a commercial programmer. So basically, doing the computer was fun, but I needed to put some software on it. At the beginning, I started with some simple 6502 assembly program, some simple register manipulation up to writing hello world on the LCD display. Then I developed some ROM monitor to be able to interact with the computer. And more or less, that's the time when I discovered the Forth language in March and April of this year. So I thought, okay, let's try to implement Forth. So for that, I read some book. I think the same book that Adrian mentioned in his presentation, the threaded interpretative languages. And also I read some article by Brad Rodriguez, which is in the core today. I think it was called Moving Forth. And also I followed a series of video on YouTube. It was called Bitwise, and there are, I think, 4 to 5 chapters about building a Forth on a RiscV architecture. But I was inspired a lot by this series. So yeah, I will give you some 6502 basics for those of you who don't know the 6502. The 6502 processor is an 8-bit CPU, so it has nothing to do with a 64-bit CPU like the RiscV. It's much more limited. And there's a 16-bit wide address bus, so it can address 64K of memory space, which will include the ROM, RAM, and I/O devices if we have. And except the program counter, which is not really a general purpose register. This one is 16-bit, all the other registers are 8-bit. So there is the accumulator, which is basically the only register that you can use. And then there's the X and Y indexes. So they are used, as we will see, in a specific addressing mode. And then there is the stack pointer, which is used to address the hardware stack of the processor. That's not what I will use for the data stack of Forth. Okay, so the hardware stack, it resides in memory page 1, so its address is from 0100 to 01FF, and there are specific instructions to push and pop values to and from the stack, this hardware stack. In my implementation, I will use the hardware stack as the return stack for Forth. Okay, so the 6502 has I think it was a dozen or maybe 16 addressing modes. So I'm not going to cover all of them, but there are 2 of them that I use in my implementation. And this one is called zero page index with X or Y. You can use both. So remember, X is a index register. In that case, for example, load A B0, that is an address in 0 page, comma X, it will mean load the content of address 00B0 plus X into A. So how does it work? Well, the base address is B0 in that case, B0. As we are in a 0 page addressing mode, it means that the real address is 00B0. The processor is going to add the content of X, which is 2. So it will take the content of B2 and put it into register A. So that's one of the addressing mode that I will be using in my implementation, and especially we will see later, I use it to address the data stack of Forth. And okay, this one is a bit more complex. It's a 0 page indirect index with Y. So what happens here? In that case, it's the example is load A, parentheses, B2, comma Y. So what the 6502 is going to do is read the byte at B2 and the byte at B3. So that's the consecutive one. And with that, it will build an address. In that case, that would be D100, and that's going to be the base address. And it's going to add the content of register Y, the index, to that base address to form the address from which it's going to load A. So in that example, load A from with indirect index with Y from B2, it's going to load 9C into A. So this one I hope the chart is self-explaining. I use why do I use this? It's in the routing for the next routing in the inner interpreter. I will store at some address the next instruction pointer. So I will need this mod to be able to read the 2 bytes of the next instruction. So now entering my fourth implementation detail. So what did I need to implement a minimal fourth? I thought, well, at the beginning I didn't really thought all these things because I went on the go, but retrospectively, I think these are all the things that I ended up doing. So I needed a very minimum set of words. So basically that's a starting dictionary, a core dictionary, a minimal program that started to run, some code to interpret that program. So basically that's the inner interpreter, and a data stack and return stack. And at this moment, having all this, I had some Forth running, but I needed to uncompile it in the code. That wasn't really interactive. So to be able to make it more interactive, I started to need some more complex code to build an auto interpreter, and having a way to look up words in the dictionary, and having also a way to compile new words. So right now I went to this step. I already have that, but at the beginning I didn't have that. Regarding design choices, my implementation is a direct threaded code, and the cells are 16 bits wide, so 2 bytes. This is what a word in the dictionary look like. So, well, I think it's quite standard. There is a header with a link to the previous word. Here, okay, here it's the code for the word here in the dictionary. So the name is 5 bytes, 1 for the length and 4 for the letters. Then we can see a jump to enter. So this block is 3 bytes because it's 1 for the opcode for jump, and then the address of enter. Then all the rest is 2 bytes per word. So the data pointer, fetch, and exit. My implementation of the data stack, for the data stack, I'm using the 0 page. In the 0 page, at the top of the page 0, I have allocated 4 variables. So it's 4 16-bit variables. And below that, all the space is reserved for the stack. The 6502 make it very convenient to use the 0 page index with X. That makes it very easy for us to address the stack. So if we look at the beginning, for example, the stack could be or would be empty. So that would be this part of the drawing. Let's say X is F6, and if I want to put something in the stack, I will store something in address 0x. So that would be really 0 plus F6, and 1x. So that would be a low byte and a high byte. If we look at this second example, there are 2 things on the stack. My stack grows downward, so the top of the stack is below the next one of the stack. Here, in that case, we have put 2 cells. So X is F2. If I want to put something in X, I will write it the same in 0x and 1x. If I want to read the top of the stack, I would read at position 2x, which is really F2 plus 2, which is F4, and 3x, which will give me the high byte, which will be 3 plus F2, so F5. That makes it very convenient to work with the stack. For example, if I want to drop something off the stack, it's simply, I need to simply increment X by 2. So it's 2 calls to ENX, increment X. sorry, I have no notion of how much time I'm taking, so I don't know if I didn't put the chronometer. Sorry.
Alexandre, we are already in your slot, in your time slot, so try to reduce and go to the end.
Okay, so I will skip the interpreter because it's quite some content, and I think
if you can show it running, it's
fantastic. Yeah, I will show it running. Okay. So I will skip the development methodology, the features, what I have right now. Well, I have some defining words, some I have the hidden, reveal words. I can do recursive loops. Well, there are a lot of things that don't work right now. It doesn't adhere to any standard, only integer number, only hexadecimal representation, so no decimal. And okay, but the demo. Okay, let's go to it. So I'm going to power the computer. I hope you can. I will try to do something. So, can you see this video here?
Yes.
Okay. Okay, I will try to have both things. So here you can see the computer. Unfortunately, the screen, the LCD screen, right now it's not showing anything. So just 2 lines are written, and the LED is on. Okay, so I'm going to enter it, or just reset the computer. Okay, so it's showing the prompt. So that's it. So 1, 2 plus dot, give 3. Okay, I can have a look at the words that are in the dictionary. So the format, I think, is not standard, but it tells us where is the header, where is the code field, and the word. Okay. And I will show you an example. So I'm going to exit the computer right now and send a small example. Instead of typing the example myself, I'm going to send it with the over the serial link. So it's going to be faster. So it's connected, and now it's sending the instructions. But basically, it's really like typing the words, just faster. So we've defined a constant port A, port DDR-A. So that's to address what I want to do here is blink the LED. So I've got a word that is off that's going to turn off the LED, on, turn on. T is going to switch the LED on or toggle it. So, okay, I'm going back to the computer. So right now, I think the LED is off. I'm going to turn it on. Can you see it?
Yes.
Okay, off. I can toggle it with T. And blink, I'm not sure if blink is going to show well on the video, maybe not. Okay. So that would be one example of the computer running. It's not much, I'm sorry. It doesn't do much calculation because it's also a very limited computer. So, and I've got another demo, which is demo.f. This one is going to write something on the LCD screen. It takes a little bit longer because it's going to send some words to interact with the LCD. What I should do later is define these as primitive, but right now it's not primitive, it's a secondary word. So I'm going to focus more on the LCD screen. Okay, I've left the code for the LED at the bottom. Okay, so maybe you can see it has written some things on the LCD. Okay, so well, that's it.
Fantastic. Excellent.
If you have any question, I'm open to questions.
Thank you very much.
Thank you for your time.
Yeah.
Well, I have just one question.
Sure.
I have just one question.
Yes.
What was it like to build that on a breadboard, and how long did it take?
Well, the thing of the breadboard, it's very fragile. So I'm really anxious every time I take it out of the box.
Hello.
Sorry? Yeah. So it's like a patience game to build it. Really, you have to be really careful, but that's the only thing I know. I don't know how to do PCB right now. So I think the next step will be to build a PCB, but that will be another project maybe for next year.
That's really impressive. Really impressive.
Well, really, I just followed Ben Eater on YouTube, so it's basically the same computer. I have just added this chip at the bottom, but really the decoding logic and everything is the same. And I've just built the Forth because I
love to see this kind of work. It's fantastic.
Right. Thank you.
It's actually still very impressive.
Yeah. Well, I'm impressed myself because having this working
has a lot of power in this kind of developments. It was used in the past almost in every new single board computer as a testing implementation, and we have lost this chance today, and I love to see that.
Yeah.
Very fine project. I have this on my agenda as well, so I'm happy you did it.
And I also ported my own Forth to another computer that was made recently. It's well, some other maker did a computer with 2 CPU. There is the Z80 and the 6502, and I ported my Forth to his computer. It's called December2020. Well, I don't have it right now to show you, unfortunately, but this one does have a keyboard interface and a VGA interface. So that was a challenge for me because I had to write some routines to interface with the screen and the keyboard and everything. And for example, when you arrive at the bottom of the screen, you have to scroll up everything. That was another interesting challenge, which I did in 6502 assembly, not in Forth. Okay, well, that's it. Thank you.
Alexandre?
Yes?
This is Christian. Just curious, this hardware design, how close is it to the Apple II clones that we had in the 80s?
Well, unfortunately, I wouldn't know because
you were not there.
No, yeah, I was there because I was born in '75, which is, I think, the same year that the 6502 came out to the market. But I was too early, and my first computer actually was an Atari STE, so it was not. I didn't have any 6502 or Z80 when they were popular. So so I don't know. I don't know. I think it's. I don't know. It's the same processor somehow, but they were using, I think, the NMOS version, not the CMOS. And this one is probably using some more recent component like the SRAM, static RAM. I guess at that time they had all different kind of technologies. But other than that, this one is very.
Alexandre, when the Atari ST came out, Forth was very popular. I used Forth on the Atari ST, and many people, it was a good time for Forth, 87, 88. After the 90s, Forth popularity went down, but it was very popular in that time.
And I never heard of that, of Forth at the time. When I had the Atari ST, I learned BASIC. I think it was called GFA BASIC. And
GFA, yeah.
Yeah, that's all I learned at the time. And then later in university, I learned Pascal and some C and that. I just really recently discovered Forth this year.
And you need to know, and all the group, that the guys from G-Forth, these are German FIC, they started with Atari ST. Ben Paisand started with the Atari ST, and I tested on that time his software over the German Forthgesellschaft. I bought the diskette. It was only sold the media. and it was very beautiful Forth, and he created, or he became from other developers. This was when Big Forth was born, the time of Big Forth for the Atari.
Yeah, and this brings back lots of memory. In the 1980, at the time, I just learned Forth, and I got a copy of the FigForth. I got all the copies of FigForth and brought them to Taiwan. And there I tried to teach people Forth, and we have a group in Taiwan. But in 1980, lots of pirates, the Taiwanese pirates, they tried to clone the Apple II. So I joined the effort with them and ported the FigForth 6502 to the Apple clones. So we got lots of fun with Apple II and with 6502 Forth on it. So that's when the Taiwanese Fig group started. Okay, so it lots of fun. But then all the pirates was banned from the United States, that they couldn't sell any Apple II in the United States, and finally they switched to cloning the PC. And PC doesn't have so much patent protection. And so the Taiwanese just, we all go off the Apple II bandwagon and jump on the PC wagon. Yeah, memory. Yeah, and then that you got a really beautiful computer there. You know, while writing that, it's not easy, but you got that beautiful board there. I really admire that.
Dr. Ting, and you from FIG, from SV FIG and Bill, you participated in all the time, in those years. And as I explained it to Alex, we have lost in this moment the possibility to make people aware that Forth is the best option for starting a new computer. If somebody creates his own, like Francois did, Francois created his own single board computer, and somebody else here in the group, I can't remember. But when you begin with a new project, the best option for you to debug all your hardware is to install a Forth.
Yes, definitely. That's the only way to start. Excuse me.
I'm sorry, I had to reboot everything to gain access again. If you pose some question, I lost them. Sorry.
I welcome Albert van der Horst. I see also Fitz is also here. Hello to everybody. Vladimir. Welcome. Vladimir Gumenuk. From where are you, Vladimir?
Hi, I am from Ukraine.
Hello.
Hello.
Welcome. Yeah.
I'm actually investigating the Forth language, and during the last 2 years, I have developed my own Forth system from scratch. Well, actually, I'm interested in Forth on 4PC.
Yeah, right. Okay, great. Yeah, welcome.
Yeah,
so if by any chance you missed the beginning or you dropped out and missed something, we were recording this session, so you can watch it later on YouTube.
Sure.
Wolf, hello. How are you, Wolf? I see also, who else is here? I saw somebody new also in the group. Well, we have a new member. I saw Ken Boak. Hello, Ken.
Yeah, Ken, also active in the chat. Right. So
yes, Ulrich.
Shall we
Go ahead.
proceed?
Please.
Is that right? Yeah. So like if we look at today's computers, then floating point is a given. And in these old computers with Z80 or 6502, there were no floating point units, and so you have to build it yourself. And so the knowledge to do it was also quite familiar at that time. And our next speaker will be Bill Ragsdale, and he will give us an update on that. I hope we are not the poor guys, but he's talking about a poor man's floating point. I'm very happy to learn about that. Bill, please go ahead.
Well, good morning, evening, worldwide friends. My disclaimer on this is not general purpose floating point. This is a floating point method used for a single application, and it used the most fundamental core concepts of floating point. So my problem, I wanted to compute large factorials. My Hewlett-Packard calculator at factorial 64 overflows. And so I was just wondering, how would you, using integer forth, do large factorials? And so my benchmark is a factorial of 100. And then to check, since the Forth I use does have floating point, I can implement it very simply as a floating point check. And then along the way, I discovered one of the interesting points of doing large factorials is they always end up with a large number of trailing zeros. And there's some shortcuts on how to calculate those trailing zeros. That's kind of clever. And then a resource on how to compute 100 factorial exactly. So here's a pseudocode. It's only about 4 words of Forth. First, we have to set up some variables, of course, and we set up a loop that runs from 2 to n+1. If we're going to calculate factorial of 100, the loop has to run from 2 to 101. We'll start with an initial value of 1, which is our formed product. And then within the loop, we multiply the product by the index. It will start out 2, 3, 4, 5, 6 and run to 100. But along the way, there'll be overflow because I'm using a 32-bit Forth. When we overflow 32 bits, we have to adjust for that. And that's where the floating point concepts come in. And finally, the program loops until completion, and we get a report. So our setup, borrowing the terminology from standard floating point, we have the significand, which is the integer portion. And then we have the exponent, which is an exponent power of 10. And then finally, the number we're going to convert, I put into input. The setup is simple. I take the number 100, store it into input, clear the significand, clear the exponent. Now we're ready to go. The output, I wrote a special purpose word that would display the floating point. So we take the exponent, we fetch it, convert the single to a double, convert all the digits with number S, and then we drop the partial result of the exponent. Stick an ASCII E in, then go to the significand and fetch it, convert to a double, convert all the digits, and then use the number greater than type to display. The overall wrapper that does the entire work is the word by integer. In this case, we set up, we process, and we output. One of the most simple, primitive computer structures, input, process, output. The process itself is the outer wrapping do loop. One is our starting value, integer value, and the input fetch 1 + 2 sets up the loop values. And then simply the do loop runs by fetching the current index, which will run from 2 to 100, make the adjustment, developing our 2 values loop, and then finally the resulting value we drop because we've already stored the significand and the index of the The action, we'll look at that in stages. The adjustment word is where all the work is done. We begin a do loop. We preserve the two values. We have the multiplicand, that is our input value. It starts at 1, and then the loop index value, first value is 2. And then UM star is a double cell unsigned product. So we're multiplying in the lower cell and then waiting for overflow. The while repeat portion handles the overflow. In this case, we have the 64-bit product. We examine the high portion. It is, with the while examines the high portion. Since it's overflowed, we then divide by 10. The 010 u/mod, the 0 converts it to a 64-bit number. The 10 u/mod does an unsigned divide. We throw away the remainder, and then preserve the value, which is our partial product as it grows. Since we've made an adjustment by a factor of 10, we then increment the exponent. This repeats because we may get more than one overflow on the same loop. So this adjustment will occur 100 times as we go through the full expansion. And finally, once this is done, we then clean up, throw away some partial values. We duplicate the significand and store it into the significand register. The same process done by a floating point is to start with the 1E0, which is the starting value, and then we just run a do loop, multiplying by the values from 2 to 100, and then the FE dot prints out the floating point. So this is my check process. Here are the results of the test. I just type in the set process and output, and we see my little output word puts out 933,26013 to the 149th power. I'll make a comment in a moment on rounding. The check value by floating point, by my internal floating point, is shown there. And then at the bottom is a check that's done by using Wolfram website, which does a lot of very, very high-powered mathematics. And we see that if you mentally adjust for all of the exponents of different values, it's all the same number. From a rounding standpoint, notice that my value only is correct to 5 decimal places, and I should be getting at least 2 or 3 more decimal places, 2 more decimal places. And this is due to the fact that the process is truncating. Every time we get an overflow, we truncate to the next lowest integer and then continue. A better rounding process, a better rounding process would be when we have a least significant digit of 0 round down, and we have a least significant digit that's even round up. Incidentally, here's an exact solution that is from the Wolfram website. And the curiosity comes about is how many zeros are there in factorials? It turns out the total number of factors of 5 is the answer. So if you take your target value, in this case 100, divide by 5, and then you find there are 20 factors of 5 in 100. But then how many factors of 5 are in 20? And there are 4. So you take your input number, divide by 5 until you get a quotient less than 5, add them up. So we get 20 plus 4 gives us 24 zeros. And at the bottom, I've taken that Wolfram value and I've broken the zeros out into groups of 5. So we have 5, 10, 15, 20, and 4 at the end. So my discoveries, 2 mistakes along the way, 2 errors. One was originally I ran my loop from 2 to 100 on a do loop. Well, in reality, that only runs from 2 to 99. And so I was off by a factor of 100. I scratched my head a couple of times because the exponent didn't come out correctly. After a couple of head scratches, I realized the do loop was wrong. So I put a 1+ in, which adjusts the index value. And then finally, as I mentioned, the loop value was always low due to rounding down. And so better to round down if least significant is odd and up if even. This is something I learned years ago in the discussion on Hewlett-Packard hand calculators, where they had the same problem and the same solution. So what we've done is a poor man's solution to large factorial. It's a single purpose solution for a single problem. However, this is the ground zero if I wish to do floating point for actual calculations. I'd like to thank Google and Wolfram for revealing my do loop error, to Andrew McEwen and Tom Zimmer, who did the original Win32 Forth, and to the Europeans for all their updates, which have brought it up to date. And the references, you can find this in a day or so. You'll find it on my GitHub site. And also at that same site, I have the Win32 Forth guide that I've written as a guide to the use of Win32 Forth. So with that, we'll turn it back to control. And thank you for your kind attention.
Wonderful.
Thank you very much. Yeah, very nice. Are there any questions?
Guess
Atle.
what? I
Atle,
have one.
make a question, you. What?
I just sit back and marvel at the elegance of it.
Brad Rodriguez then. Brad Rodriguez.
Bill,
Fire a question.
thanks, you're the one who makes me understand integer maths in computers. But was there any other way of computing other than floating and integer with computers?
I didn't consider any others. I'm sure there must be. Let's see, I had another thought which totally vanished.
Albert is raising his hand.
Yeah.
Albert van der Horst is raising the hand.
I want to make a remark. I recommend the Win32 Forth guide from Bill Ragsdale on GitHub. It's really excellent.
Oh, I just had my thought came back. One of the beautiful values of Forth is you really have to understand number representation. And they're powerful concepts, they're very simple, but the number circle, operating in a 16-bit world, 32-bit world, worrying about sign extension, all of these things are handled internally in the higher level languages. And in Forth, we have to cope with them directly. And it really forces us to understand structures, how numbers are represented, why they're represented. And so I had to jiggle around back and forth several times, getting the right combination of unsigned arithmetic, signed extension to make this work. And you really understand computer math once you've done a deep project in Forth. So thank you.
Thanks, you make me appreciate maths.
Right. Are there additional questions?
Brad Rodriguez is in complete silence. I can't believe.
I should say something?
Yes, we need your input.
I was just going to type a note to Christian that I know there's at least one other number representation, which is called big num. It allows arbitrarily large numbers and basically variable precision or completely extensible precision. I've never worked with it. I've just heard of it. So I thought I'd throw that out there.
If I remember back in Fourth Dimensions, years and years and years ago, somebody came out with a innovative variable precision number series. It'll be buried back somewhere in fourth dimensions, probably about 1978 or 80.
Oh, I got one question. Have you thought about how to normalize it?
I'm chuckling here. The application you saw here, I did in about an hour and a half. And my irritation was that there are 3 examples I put on the screen, and they all have the different exponents. And so normalization is the next step to get some sort of uniformity in the exponent. Typically, exponents are done in multiples of 3. And so on my little primitive work here, the normalization would be the next logical step. Thank you.
Don't a lot of financial systems use BCD?
I don't think in the last, I'm guessing, but I don't think in the last 20 years they do. They may be ever since maybe as the days from Grace Hopper onward, maybe use BCD, but I don't, does anybody here know anything about actual use of BCD in computer system? I will point out the 6502 does have BCD arithmetic. You can set a flag on that and your arithmetic is BCD.
Yeah, all financial programs use integers rather than floating point.
Sure.
For accuracy. So that's probably the main thing. But the floating point is fantastic. Great stuff, Bill.
There was a legendary Turbo Pascal version with BCD arithmetics in the 1980s, I remember.
Mm-hmm. All right. Any more questions? Okay, then Bill, thanks again. Nice to give us some insight. And yeah, shall we proceed to the next talk?
I can present Dr. Ting.
Sure.
He will show us the Forthmobile. No, Forthmobile is from Atle, sorry. Dr. Ting will present the virtual Java machine or a real Forth machine. That's the question.
Okay, thank you. Let me grab the screen, and I will do the share sound and the share. Okay, let me see the show. Okay, I hope you see the screen. Yes, we do.
Yes.
Okay, good. Yep. Good. Okay, so this this presentation is Java virtual machine and Forth virtual machine, or what I would say a Forth real machine. Okay, and I would go through the CPU architectures just briefly, and the RISC architecture, and make a few comments on the bytecode. And 8080 bytecode computer, that's the new bytecode computers, and then it evolved into the CISC computers. And then I would venture into the Java for a virtual machine. And I think the Java bytecode is a good computer architecture. And if I take that architecture and implement a Forth on it, that's what I want to present. Okay. So there are many different architectures. We used to design CPUs for about 100 years now. And architecture is precisely prescribed by its instruction set. All instruction sets are complicated, even in the RISC architectures. Among the RISC architectures now, the ARM architecture is now firmly established. And the RiscV is a rising star. It's, as you hear from our first speaker, it's a very popular design in the FPGA and the new microprocessors. And but all these instructions, although they are reduced instruction set computers, they are still very complicated. And the example is the ARM instruction set. It is a mess, okay, and it is not reduced by any means. And then the RiscV instruction set looks much better, but it is still complicated. Okay, you got 4 different types. But so I think if instructions were limited to bytecode, we could have simpler architectures. And 8080 was the first successful bytecode computer because most of the instructions are in bytes. It has byte instructions with up to 2 bytes of optional data. So here is a picture of 8080 bytecode. You have 1 byte of instructions and 2 bytes of additional data. And the opcode is interesting in that in 8 bits, you have 2 opcode and 2 3-bit register or opcode. So it is a very interesting way to microcode the instructions. So here, the first 2 bytes actually defines 4 groups of bytecode: register, application, move, and ALU, and then transfer and miscellaneous operations. So here is a picture of the 280 bytecode of the 8086. It is pretty busy, but it did well with the 1 byte instruction. So 8080 was a very clean 8-bit CPU, but Intel extended the instruction set to 16-bit, 32-bit, and 64-bit CPUs and made a total mess. That mess was codified with the name CISC. However, I think some at least make an effort to redeem the mess by Java bytecode specification. So in Java virtual machine, it handles bytes, short integer, regular integer that's 32-bit, 16-bit, and 72-bit, and the long integer, which are 64 bits, and floating point number, 32-bit, the floating number, and the double floating number of 64 bits. It uses a data stack, and each function has 4 local variables. It uses an implicit return stack, or what we call frames, to invoke functions. In the Java code, it has a 8-bit bytecode, and with optional mostly 2 bytes of additional data, and sometimes it could have 4 bytes of optional data. And the code map is interesting in that it's fairly packed, but it has about 50 slots not used. And it defines all the possible operations with the byte, short integer, regular integers, floating point numbers, and also the double floats. Okay, so it is a fairly good design of a CPU which would handle up to 64-bit double integer, double floating point numbers. But I was looking at this and thought that there's actually a virtual machine in that big map. So I'm trying to develop a fourth machine based on the Java bytecode. I just pick up the instructions which are dealing with integers and ignore the long integers, floating point, and doubles. So I try to conform to the Java specifications as much as possible, but I only use the integer. I only use integers. And it uses return stack frames for nested function and for local variables. So if you look at this bytecode, it's the same bytecode map as a Java virtual engine, but I just don't do any of the long integers and floats. Okay, so it's much a sparse map, but that's enough. That's good for a fourth machine. The only thing I missed in the Java virtual forth are the instructions which deal with the return stack explicitly. So I need do next for the loop, and I need to load the long or 32-bit integers, the literals, and I need to push and pop on the return stack. So with this additional 4 instructions, I can implement that fourth machine based on this instruction set. So I can map the fourth virtual machine to Java fourth machine with the ALU, plus minus, multiply, divide, mod, and negate, and some a few more. For logic, you have AND, OR, exclusive OR, left shift, and right shift. And to operate on the data stack, you see the Java has a lot of stack operations that we just learned. And to access memory, I have fetch and store, which has native JVM instructions. CFetch, CStore, and WFetch and WStore. Sorry about that. This is for the 16-bit integers. And for branch, Forth, we only need branch always and branch on 0. But Java has a lot of branch options, conditional branch. And the call, we can use the invoke virtual, and return and exit are both return instructions from the Java virtual engine. And the return stack, that's what Java JVM doesn't have. It has rfetch, okay, but don't have the push R or pop R. The 2R are pop. So this thing I need to add, and also the do next, which I needed to make loops. So all this fourth virtual machine was synthesized on the Quadros 2 IDE from Atle and now Intel. the fourth virtual machine core runs at 100 megahertz on the simulator. But if I add a multiply, divide, and the barrel shifter, it slows down significantly, and it runs only at 20 megahertz. So here, the fourth auto interpreter was assembled, compiled, and simulated on F#, my favorite fourth on PC. And the dictionary is very tight. It's only 3,424 bytes. And the code fields are mostly executable Java bytecode. So it is a very nice implementation. Let me see. Okay. Okay. Some of the results from the simulator or the synthesizer. If only with the 32-bit core, it took almost 4,000 advanced logic units in the implementation. If I add the multiply, divide, the logic unit count rises to 5,000 some. And if I add the barrel shifter, it's 5,786 logic unit. In conclusion, Java is a good hardware specification for a bytecode CPU. And fourth virtual machine maps well to the initial parts of JVM. And a fourth real machine was successfully synthesized in Quantus 2 for a Stratix 2 FPGA device. But I don't have a board which has a suitable FPGA to test it out yet. But I think the synthesizer and the simulator said that this implementation is workable. Okay, let me just stop sharing and see if there's any questions. Okay, thank you very much.
Wonderful, Dr. Ting. I need to say this theme is fantastic. This is absolute brilliant presentation, but we had a problem with the audio and I could not hear you very well. Probably your mic is very high in the control because you are distorted. Your sound is completely distorted.
But I think the slide should be quite clear.
Sure.
I'm sorry.
We could understand everything and it was fantastic. I wish we had a new opportunity and you make a better audio, only that, but it was clear.
Okay, thank you.
Our next speaker is, sorry, are there no questions for Dr. Ting? Atle, do you have any questions for the Java machine or Dimitri or?
Christian has one.
Okay.
Dr. Ting?
Yes.
Are you still there? This is all running on the Java virtual machine. And the size of the fort running on it was more or less between 5K and 6K. How big is the virtual machine itself and the Java behind this running the fort?
I don't know much about the Java machine which runs the programs, But on this one, if I just implemented the all the instructions I needed in the Forth machine, you know, it is the dictionary is only 3K. Yeah, that's the auto interpreter. That's what you can see. But behind it, it's the hardware implementation. And for that particular FPGA, I need about a 4,000 to 5,000 logic unit. But how complicated is that logic unit? I don't know.
Thank you.
Well, I got one question. Would it be possible these Forth programs that you create for this JVM, could they be decompiled into Java code?
It is already about Java bytecode. It's exactly Java bytecode, okay? But that Java code may not run on a Java virtual machine, okay? Because I took the exact, I'm trying to conform to the Java specification as much as I can, but I could not, okay? There are differences, different requirements in a Java Forth machine, which a Forth virtual machine does not have. Okay? But on the outside, it looks exactly Java code.
I have a question. There is a similar bytecode under Python. Does that qualify also for making a virtual Python machine, or did you have didn't you look at that?
I didn't quite get you. Could you repeat it?
The code of Python is similar to Java, the underlying bytecode. Does that qualify usable for Python or a Forth virtual machine based on Python?
I don't know about much about Python and its engine, the engine behind it. But this project, what I'm trying to do was to see if I can actually implement a Java real machine. Okay, took the Java specification and try to turn it into hardware. But it's I still don't fully understand the Java specifications, and I found there's lots of things that doesn't how to implement. Okay, so I just took what my understanding of the Java code, my understanding of the Java machine.
I see Brad Nelson added something on the chat. Brad, do you want to say something about this?
Oh, no, I was just adding the link to the Python bytecodes if you're interested to compare. That did seem an interesting. It looks like it's yet another virtual machine, so not sure there's, but yeah. And it has some things that are very, very that are higher level than Java bytecodes. So things with slices and whatnot. So, anyways.
Yeah.
Okay.
Okay.
Dr. Ting, can we get the slides for download?
Sorry.
might you provide the slides you showed us for download? Did you upload it to your account, your Google account or so?
I really can't hear you.
He's asking you to
Anybody
upload
help-
your slides somewhere, Dr. Ting.
Yeah, my hearing is not.
No problem, no problem, Dr. Ting, no problem. I try to help Rolf later. I have some links. I try to help you, Rolf, with that question.
In any case, there will be the recordings, so you can review the talks and then also have a look at the slides. So that wouldn't be a problem.
Fantastic. What do you think about a Norwegian Viking that we have in the group and wanted to conquer the automobile sector with his Forthmobile, Atle Ramsly from Norway?
All right, I'm going to try and play a video for you, which hopefully would show how easy it is to program a robot in Forth. So let's see if I can get this to work. Now I need to share my screen. I need to find the correct window to share. And then I gotta hit play. Do you see a picture of me on the screen now?
Yeah.
Yes.
Okay, here we go.
I think you need to share your audio on Zoom. There is a button below to share your audio.
Now
I'm
let me
also only
see.
seeing 1 frame per second.
Okay, let me see if I can fix this. More.
Instead of sharing.
Hear sound, yes, and okay. Now then, let me go back and try again.
No audio, Atle. It's muted.
I think there's an option in Zoom to share a video instead of the screen. Maybe that would work better.
Oh, can I do that?
I think.
Yeah. Oh, absolutely. Let me see if I can. How do I do that?
When you go to share, I think there is an advanced button on the top.
Okay, okay.
Yeah.
Advanced, yes. Okay, excellent. Aha. Okay, computer audio content from second camera and portion of screen.
Is there not a video option there?
Content from second camera, it says.
In my case, I've got PowerPoint, portion of screen, computer audio, video, content from second camera.
See. Optimally just Okay, let me try a portion of screen and see what happens. No, this is going nowhere. This is going nowhere. Let me. How did I get into this mess? Okay. Well, then I'm going to do it in a different way. I'm gonna wing it if it's if I can get my screen back here. Oh man. I think my whole computer has Zoom is not responding.
Atle, I was proposing we continue with Brad Nelson and later you return after you try again.
Yes, because I lost my whole thing here.
Yes, okay.
I'm going to try this again.
Well, we have Brad Nelson with us, and we can start asking Brad about what he created with ESP32 Forth, the new implementations. If you want to tell us, Brad.
Yeah, apologies for not making it to this group for the last many meetings. Life has been busy, and the meeting is early in the morning, and it's been challenging to find the time. There has not been a ton of change. I can give a little demonstration of one thing that I've added recently that might be of interest to some folks. It's not typical for a priority, but for Forth folks. But a floating point is something where it is often useful to have it, and so I put in the basics of adding floating point to. Can we see my screen? Is that yeah? So the if you get the very latest version off of the website, it's been up for a little while, but I haven't talked about it anywhere. So I've added sort of the core floating point words. It's single precision floating point because the ESP32 does not actually have hardware double precision floating point, and so there's not a ton of point in that. The main reason I added it is that I have been very slowly in the background tinkering on thinking about bringing small machine learning models to the device, and I'm imagining that for some of those I will want to use floating point, and there are most likely for those for performance there'll need to be some tight kernel that will be done in a more lower level way, but you'll want to be able to communicate inside and outside with Forth. It ended up not being too bad to add the floating point to the system. The amount of total change was actually fairly small, and so for the moment, although there is a big master switch to turn it off, it's on by default. And so to give you an idea, I'll just even take a look at the code that was added to do it. This one little section, adds in the notion of a floating point stack, and there's a single additional variable that holds the floating point stack pointer. There is no caching of the top of stack. So it's just a pointer into the very top element, and it just implements sort of the core words. One design consideration, I'd love feedback on this point, is that for the time being, I didn't, because it's a single precision floating point stack, I used for load and store SF add and SF store. So I haven't defined F store and F at because there isn't the double precision one, and I wasn't confident that it wouldn't introduce more confusion to have an explicit, to have a single precision floating point stack only for it. But so it's just the most basic arithmetic ops are there. And then in terms of hooking it in, it wasn't too bad. There was a little bit of there's a couple of additional words that get glued in for a floating point convert, and then in the core of the interpreter, I just had to add this FP pointer, and then let's see, there's one other spot, let's see, I wanted to show here. Yeah. So yeah, in the core, is where this F convert routine is implemented. So this is doing the work of parsing a floating point number, and I did that the reason I did that in C is because I wanted to add it into the bare system. So when it's doing the most basic evaluate, it attempts to first do an integer conversion, and if that fails, it tries to do a floating point conversion. I've used the convention from eForth and others where the floating point values have to contain an E. So to give you an idea of how that works, if you do 3E and 3E and 4E, those are putting floating point numbers on the stack, and if you do an F divide and print, then you've got your numbers there. So a 1.3 doesn't work, but a 1.3E does. Let's see. There's in higher level Forth words, I've defined a little bit more. So there's F variable and F constant. And I've done that like a square root as well. That's done in higher level Forth. So just the starts of it, but enough that you could use it for things. And beyond that, there hasn't been a ton of churn. One question I have also for folks is it's been a little bit while, with the exception of the floating point, which I think was added many months back. Actually, things have been relatively stable in the beta version, and so I'd be curious if folks think that we are safe to migrate the beta version to stable and sort of make another cut. And I'd love questions or comments, or yeah.
This is fantastic, Brad. Excellent. I don't have much feedback from people in the group with ESP32 Forth, but we have new members to the group. Guido Lewalder, are you there?
Yes, I'm there.
Guido, you installed yesterday or this week ESP32 Forth.
Yes,
How was it? How was it?
The first time I had a messed up screen because of this carriage return and line feeds.
What terminal were you using? Was this the Arduino terminal or something else?
I'm using Putty, or the version of Putty which is named Kitty.
Ah. Yeah, it's tricky to find good defaults. I picked defaults based on what work in the Arduino terminal, but I myself use PuTTY on occasion and find that I had to set up a separate config to make it work. This is a sort of a it's tricky. So did you find settings finally that worked, or was it challenging?
Yeah, I find the settings. This is a setting where every line feed gets a carriage return, or every carriage return gets a line feed. And then it worked. But I have the problem that I have a terminal with FOBGL on a VGA32, and there's the same problem without these options in PuTTY.
Guido, you have a TTGo board and you wanted to know about VGA also.
Yes, I did read that the system at this time, the ESP32 Forth computer does use the BitLooney connections, but on the web page, the source does use FOBGL library, but I can't find in the source code of the ESP32 Forth the lines for defining the pins for VGA.
Well, this is for Dimitri. This question is for Dimitri.
I'm not sure I fully understood the question. Was the question if there's a file where the BitLooney libraries have been added to ESP32 Forth?
Peter told me that ESP32 Forth does use VGA, but I can't find any lines in the source where it's defined where the pins are for BitLooney or for FOBGL.
Oh, okay. I see. It's the pins you're wondering about, how to set the pins so that they are correct.
Well,
okay.
Here, if you enter the FORTH2020 ESP32 page, project number 5 is of Dimitri. So you see ESP32 Forth and PS2 interface. So this is the GitHub of BitLooney, but you don't need to install BitLooney because Dimitri did for you. So you press here this button and you enter into the GitHub of Dimitri, and you need to download this one. I am correct, Dimitri?
Yeah, that's correct. And that actually has the correct pin mapping for, let me try and pick it up. If you've got the TTGo VGA 32 board, it has the correct pin set up for it in there. I don't remember for sure whether you have to install BitLooney separately. You might have to, but
no. It's already almost here, or everything is here, I think. Okay. You need to install into Arduino. That's
what I think you have to do. Yeah, I think that's the part. So maybe I can write some steps on there about how you do that.
But okay, basically, Guido, you go to the page, download the file of Dimitri. Both of you have the same TTGo board, so it's just plug and play and download the software and it should work. It's okay? It's correct?
That sounds correct to me. Yeah, there's not much else to it. That will give you at least the libraries, and then the rest of it is more to do with the keyboard setup. So I have some keyboard drivers as well. But the keyboard drivers they're not always reliable, but you would definitely have the BitLooney libraries that way. So yeah, keep keep in touch and let me know how you do. I'll put the link
Dimitri, keyboard is always complicated. The PS2 standard with these Chinese keyboards are not so easy to. There are sometimes ghost, phantom keys, and so it's not. It's a more electrical problem than a software problem.
I see what you mean. Yeah, that's been the weakest part of it, but the libraries work just fine. I'll just gonna paste it in the chat.
Sometimes if the library allows you to add some milliseconds on the charts, routines or so, you can fix normally for every keyboard on the market. But in other cases, probably Vitturi has a recommendation for what kind of keyboards you should go after.
Yeah, I think one that I found works, FabGL works more reliably in general. What you can do with FabGL is actually really impressive. If I show the page for that, I think this is it. If you can see the FabGL, where is it? Yeah, you get like GUIs and stuff like this. They're so impressive, and the keyboard works fine. I mean, you can even emulate these old computers and stuff.
Yes, but this is not ESP32 Forth. Nobody created the interface.
Well, I was using FabGL originally when trying to get the graphics, but I disliked using it because the library is so big and so complicated that yeah, I just kind of gave up on that. But to be honest, a little bit of work and you could do it as well. Maybe that's something I can upload to GitHub. It's going to be kind of incomplete, but if someone wants to get started with the FabGL libraries instead, that could be the way. Or I think Pablo used FabGL.
Yes, Pablo is using FabGL.
But for I forgot his language, a different language.
Yes, Reda 4
R3, right?
Yes, it's not the 4 used by the SP22 community, but it's a translator of my other language, the R3 Forth. And the basic idea is make a autonomous computer with the SP32.
Well, I actually played around when listening to Dimitri's presentation some months ago, played around with LilyGo, TG, whatever, VGA board. And I adapted the ESP32 Forth to actually output its terminal output on the VGA and accept PS2 input. So avoiding all the graphics stuff that FabGL provides, but just doing character-based I/O. And I can just paste the link. I put it on GitHub. And so it's not considered to be a competitive in any way, but just my experiments, what I did. And it's rather nice because you get a little small Forth computer that way.
Well, this is fantastic. If you have this link, Ulrich, Guido can of course try it.
Yeah, sure.
But share the link. Share it, please.
Yeah, it's in the chat right now, but it's GitHub. You have to do things on your own. Like
I need to tell you something. I have the VGA cable prepared since months. I never tried it on the ESP32. I will try it, but what is the problem? ESP32 is a microprocessor, so I use it to control different things. I don't use it as a computer. But if I want to use it as a computer, I have Wi-Fi. And Brad did a web browser interface, so you have a computer inside, so you don't need cables. You work like in a computer. If you put cables for VGA and keyboard, you are emulating the same that the chip already has inside. Thanks, Brad. This is why I never use it.
One thing the talk of these extensions has made me think that I wanted to highlight, especially as this group is filled with folks who've been doing cool things extending the system. I put in a hook a little while back that I think might be useful for folks extending it. There's an optional include, so that it will attempt to include a file called user words. And it, by default, has this capital user words defined, and that allows you to, if you want to place your extension in a separate file, you can then place it in the source code alongside there, so that you don't have to constantly be editing the main source file and
yeah, very nice.
So. Not sure it will work for every use case extending it, but it's another option if you want to have something that you don't need to keep in sync and so on.
This is very important probably for Atle. I don't know, Atle, if you want to present, or we do it for another meeting.
Well, I just found out that I don't have this share video thing, so what I could do, I could quickly go through just showing what the Forthmobile is, and then looking at some source code that shows how to program it.
Excellent. Yes, perfect. If you
okay,
agree,
then I will do that now. This I can do simply by sharing one window. If I find the right one, and this is the right one. Now you can still hear me?
Yes, perfect.
Okay, so yeah. So to build the Forthmobile, it should look something like this, with an ESP32 and some other items on it. This is the motor controller. These I have mounted 3 of these laser rangefinders on it, and 1 compass, and I have a place for mounting a GPS system on it. That's the input to the system. Then there's the ESP32. Then I've made a board for it, so I've broken out things that I need in order to connect it. Then I have here's a link to how to get started with this, all the software and tools that you need. And that's here's a simple program, how to blink the lights on it. So I have a constant for on and off. I have 3 pins that I use for these three laser distance meters. Then I can shut each and every one of them on and off with these 3 words, and that will make these LEDs here blink and activate and deactivate these 3 sensors. Now, in order to access this from Wi-Fi, you need to add a file called autoexec.fs to the SPIFs directory. I upload those using using the ESP32 data uploader, and I set an SSID and a password, and then I start a Telnet server. And from then on, I can access it over Telnet. Then I need to access the motor, the 298 controller. So I define constants for all the pins that are on that controller. Then I have some constants for directions. And then I set them up using these pin modes that everyone should recognize from the Arduino IDE. And then I set a speed on each of the motors, one for the left side, one for the right side. Then I have one that puts them both together, so I can go in a straight line forward or backwards. Then I have the most important of all, that's the stop. That's when it's doing things it shouldn't be doing. And then I have what I've called the gearbox. That's just initializing these pins that are also used for servo motors, so that they will go either forwards or backwards. And then I have one that sets these gears. It's called drive. So it sets the left and right speeds, and then it sets the direction forward or backwards. And then it just, this is how it works. It just gets that value of the stack, sends it to the left, and hold on, it sends the direction to the left and right, and then it sends the speed to both motors. And it can also turn on a dime. That's the motor, and then it's the auto drive. So all of these get uploaded. I upload it using this upload extension to the Arduino IDE. So here it's about obstacles. Does it see an obstacle on the front, on the right, on the left? I also take care of these values, because even if you tell it to go in a straight line, it won't do that. It will always go to one side or the other, because these motors, they don't turn at the same speed when you give them the same PWM value. So you need to somehow make sure that it stays on course. Then I read all the sensors, and then I correct the course. So I read the course from the compass, and then I compare it with the course that we want, the desired course. And then I just subtract it, and then I do the correction here by adding to the left or right PWM values, and that should hopefully get it back on the right course. And then when it sees an obstacle, then it will back off and stop. When it sees an obstacle to the left and to the right and to the front, then it will not do anything else. It will exit the loop. You'll see that later. If it sees an obstacle to the left, it will try to turn away from it, and the same on the right. And here is the main loop. So it will read the sensors. It will initialize both speeds, left and right, to 200. It goes from 0 to 255, and then it will give the command to start driving. And then here is the loop. It will plot radar values. That's for an application that I've developed for a mobile phone that I'm not really finished with, but it will plot like a radar screen on the mobile phone. I thought that looked kind of cool. Then it will read the sensors, correct the course, decide the action that I showed you up here, avoid obstacles, and if it's boxed in, it will stop. And that's all I had for the code. I think I can show, perhaps I can show it actually driving. I might be able to do that.
Well, you can show the video without sound if it's driving.
I should be able to show it without the sound. Yes. Hold on, if I can.
Ronnie has probably some questions. He's interested in robotics. He did this.
Yes, sir. Sir. So maybe it's not is a question or not. When I try to coding with Arduino IDE, we use pin mode, we use blah blah. But here I see Forth code sequence is totally different with Arduino IDE. Am I right or wrong, sir?
Yes, what you have to do in the IDE is that you have to load the program that Brad just presented, and that is an INO file. And then to that INO file, you have to add the libraries that you will be using. Yes. And when you've done that, you need to add some macros to the INO file. This is not overly complicated. You will get a feel for it when you've looked at it for a while.
And
then
in the end of the demonstration, I will show installation very briefly, very rapid of the ESP32 Forth.
Yes, well, from that point on, you can start adding the codes that I just showed you. And you can upload those, you can change them if you need to. If you made a mistake and you uploaded a code with an error in it, you don't have to reflash or anything. You just upload the correct code again and it will overwrite the old one. Did that make sense? Sorry. Hello?
Yes, sir.
Yes.
Okay.
Now I will try to show. A video that should show how this works. Let me see if I can share the screen again. Find the correct window. Can you see a picture of a robot and a screen now? A screenshot?
Yes, yes.
Okay, well here you should see it. How it's done. First you connect over Telnet, and if you get first you turn on the Forthmobile. That's very important. If it's not turned on, it won't work. Now it's on, so now you should be able to connect to it, and then you can type in the commands directly. So you control it just like you would control a terminal, like you type in things at a terminal. That's exactly how it works. And now you give it instructions to go forward. And to stop. And those buttons that I'm pressing there, It would be the same if I just typed the commands in at the prompt there. I just added those buttons to make it easier. So that's one video that shows how it works. I have another one here that manipulates the servos. So I'm just loading that. And then I'm uploading that to, you upload, this is what you upload. What you see there, it was marked, that's all you need to do in order to reprogram the Forthmobile. So you don't flash anything, you do this while it's driving. And then you can take that code that you just uploaded, and you can execute it to make it look left and right. That is something that was coded now in the last seconds. So that's what I had.
Delightful. That's very impressive and very beautiful code, actually. Yes.
Very cool project. Yes.
Yes, sir.
So did that make sense at all?
Yes, sir. Yes, sir.
Yes, it did.
Very nice.
Excellent, excellent.
Could I ask you a question, Atle?
Yeah, sure.
You gave me the itch to build my own with all this, but it's hard to find parts here where I live. I have to wait 2 to 3 months to get anything from China, or pay 3 or 4 times the price in Montreal.
Same problem here.
Could I start from a toy sale after Christmas and get one of those 1 foot long toys and work with this? How do you feel about the idea?
Well, what I did, I bought all these different parts separately. But what you can do is you get those kits. What I did here. This is a metal plate. That's not necessary at all. You can get this and this as a kit, as a plastic kit. Then you buy that motor controller, and then you buy the ESP32, and then you should probably, I have a proto board here, but I've also made this board, which is a lot more reliable. So I plug the ESP32 in here. I plug in the sensors, and then I'll just 3D print a plate to put on top of this chassis, and then I'll mount this on top of that plate. That's how I do it. So you could start with any kind of kit that you can buy in a store. It doesn't have to be identical to this. It must have the motor controller, unless you want to program that from scratch again. And it must have an ESP32 and some way to hook it all up together. But
see, I have something to get started. So I don't know if you'll see this, but this is a CNC controller that a friend of mine built. Okay, and it uses the ESP32, and it's got isolated outputs, and it's got the solid state relays that you could put in there. And so I could probably, and access to pins on the side. So I could probably use that as my motherboard.
Absolutely. I mean, you're an electronics guy, right?
Well, mostly I'm a hardware guy.
Yeah, so you'd have no problem figuring that out.
Christian, have you visited the Robot Shop Canada? Robotshop.com, they're based in Canada.
A few times. I think my friend for his CNC got some parts from them.
They seem to have everything you need.
Oh, so maybe I should take a look at that, because I'm just not doing anything with hardware, because anything I order takes too long to come here. And let's say I'm cheap. I don't like to pay 3 times, 4 times the price.
I get all my stuff from AliExpress, and I'm so used to waiting. I have a second board that I've started to. It has a lot more I/O. It has some registers on it so that I can get more I/O out of the ESP32. But this is as far as I got, because now I'm waiting for sockets from AliExpress. That's patience is a virtue when doing this. Or you have to have a lot of money.
So, Christian, you are the next to present what you do with ESP32 Forth. Are you ready or later?
Okay, I could go ahead. So let's see
Fantastic.
how we share this. Are you seeing my screen now?
No, not yet.
Okay, maybe I should click on share. Is it
Yes.
there?
Yes, yes.
Okay, I'll move something out of there. So essentially I'll tell you a little bit about me. I'm mostly a hardware guy. I graduated as a technician. I worked all my life with telephony, computer networks, telecommunication, network management. All the time I was using terminals to control other devices from a computer, but I never really understood the programming part of a computer. I fixed them, I replaced parts in there, but the programming part was not there. So I'm trying to, with ESP32 Forth, I'm trying to fill up this need to understand. So my experience as a beginner, you just had it, but I want to tell you about what it felt like to use ESP32 Forth. I want to show you what's available on FORTH2020 site to get started with ESP32 Forth. So what did I use as a hardware? The Arduino IDE environment 1816 and a Windows 10 running on an AMD PC. The Espressif ESP32, that's the board manager that you have to install. Do it ESP32 Dev Kit V1. This one worked without any effort right from the start. The ESP32 Forth version 705, I think I used 705.4, but it worked just fine. It's also nice to have some other tools. My basic tools most of the time was just a lead probe, just a resistor soldered to a lead, a ground wire on one side and the tip touching a pin to see if it lights up. So I had a multimeter. Sometimes I didn't trust the lead pin, the lead probe, so I double checked with the multimeter. Don't forget it. In amp mode, you're gonna blow the pin. A digital memory oscilloscope. I would love to have one, but all I had was an analog one, so I took pictures. Logic analyzer would be great to have, but they're not essential. Okay, what I found to be essential as a beginner is to keep it simple. They say keep it simple, stupid. I prefer to say keep it super simple. I don't like to feel stupid. Yeah, our goal here is essentially to start to familiarize ourselves with Forth using the ESP32 Forth available and all the information available on FORTH2020 site. To keep it simple, minimize the hardware involved, minimize the software involved, minimize the complexity of the development environment, minimize the complexity of any other support software. Minimize the number of things you have to learn in general. You say what we want to do is learn Forth. So we don't want to debug all kinds of other things. When we're ready for it, when we know the basic of Forths, we'll add more complexity. Okay, the way to apply KISS for me, use a simple Arduino IDE. I had been exposed to that and I could use it. Use a simple serial communication port and terminal emulator. In my case, it's Teraterm at the beginning and Eggshell now. Stay away initially from complex protocol like I2C, TCP/IP, Wi-Fi, web servers. Sometimes I couldn't get it to work and it was just discouraging me. So I stuck with the COM port for quite a while and I'm still using it. Start with a simple software project like Blink. Yeah. When you come from the hardware world, you really never had to program much except with BASIC on my ZX81 and assembly for a few adaptations between my Apple II clone and my ZX81. So Forth convinced me that it was simple enough for me to give it a try. So the Blink was my first attempt. Write a program in human sentence first, because this is what humans understand best. Before I can write a program myself, I have to write it in human words. I write instruction as if I was talking to a human. Convert the human language procedure to Forth words that express what you just said in human words. That's what I like about ESP32 Forth. It's close to a human language. So if I use certain human words in my language, would it be French, English? I can just pick a word that is similar in ESP32 Forth and it will have a meaning for me. Use a simple editor that you're already familiar with. Sometimes I try to use some fancy editors that were used in fancier IDEs, and I only got confused with the editor. Something I could master was my old Word and Notepad+. Document your programs with a lot of comments to refresh your mind later. Yeah. You'll probably leave your project aside for a week or two and you'll come back later and you'll try to figure out what you did. You'll be happy you have those comments. Test each word created before creating other words. Forth is building word over word. You create words and you use those words to create another word and you use that newer word to create something else. Everything that is at the base should be working, otherwise you'll have a hard time. A few recommendations for yourself. Yeah, you're the one doing all the work. So take a pause frequently to refresh your mind. Be patient and think positive. It takes time to learn something well. Get assistance from FORTH2020 members if required. They're helpful and they'll be glad to help you. Motivate yourself by sharing your experience with others. Sometimes I didn't feel like doing it any more Forth when I started sharing it gave me motivation. Congratulate yourself when you succeed. In my case, I pour myself a beer. Sleep well. The inspiration might be better tomorrow. Have fun programming with Forth and learning. So what do we find for ESP32 Forth on the FORTH2020? Well, you find on FORTH2020, you'll find the Forth Home first, and in there on the left, you have all kinds of things that you can pick. Yeah, and this is example of what you could find now, which ESP32 to choose. How to use the Arduino IDE, how to download the ESP32 Forth. It's all there. It will be very helpful. And if you have questions, don't forget that the group is there. Now, before you do anything with Forth, you'll need vocabulary. You'll have to know the words. There are some basics to learn. And I feel myself that this place here on the on FORTH2020 is the place that gives you the best coverage of all the glossary, all the words. A lot of this is higher level. I feel myself that the basics is the word, how to define a word, how to make comments, how to control memory, how to control the stack, some basic maths. After all, we have to calculate a few things, make comparisons so that we could make decisions with logic, have looping controls, and finally you want to do something like blinking a LED, character IO and input output. So do not worry with the advanced hardware or software of ESP32 Forth. Stick to the basics. Once you know that, you'll be able to use the harder stuff later. So ESP32 Forth experiments for beginners. I wrote quite a few of those, mostly going along trying to learn. They're not tutorials, they're the testimony of my experiments. So the Blink experiment project 61 is the one that got me started. Everybody starts with the Blink when he learns a new programming language. So go and give it a try. Here I'm giving you a summary of what it looks like. This is what I use, my good old ESP32, the dev kit V1. At the time I had a power supply problem, so I had to use an external power supply because I blew my power supply on the board itself. My terminal emulator, that's the X shell that I use. On the left side, I see the result of entering commands on the right side. Some preliminary informations that I basically tell you here that you need a colon and a semicolon and put some words in between and a word name. So I created very simple words like LED setup. Like in most programs, you have to set up things. So the LED setup does the job of configuring the LED so that it could be used as an output. Create words to turn the LED on and off. Very simple words. One call LED on. The arguments that I provide, yes, don't forget it's all postfix. And then the pin, which is the command. So pin uses high-end LED, and as a matter of fact, it's essentially an alias, another word to say digital write. So create a word to make the LED flash constantly. Now I reuse the word I just created. LED flash 1 will use LED setup.
Christian, how long does it take? Because I am after you and
another 2 minutes.
I will be okay.
Maybe 1. So that's about it. Okay. The LED flash 1, I could show it to you. I hope so. So you should be something, see something flashing. And I think that you've seen enough. I also created one for called Let Flash 2, and it could flash as fast as I could. That's what it shows. It looks like on this scope, and the frequency was about 575 kilohertz. So have fun programming. There's a lot of more beginners experiment on the site. You'll find a timer experiment, an encoder experiment, another experiment with the encoder with interrupts. You'll also find some more advanced stuff like adding words to ESP32 Forth, wire vocabulary. Before you start using I2C, you're going to have to figure out how to use wire. ESP230 Forth, that was my first experiment with wire. I had a temperature sensor and thermostat, the LM75, and I used that as my experiment. So my conclusion, well, here is what I think about ESP32 Forth. It's simple to install. It's stable in the current version. It's fast and flexible. It's motivating with the interactive feedback. Okay, it's lacking a few of the features of actual languages, but it's capable of extending itself easily to compensate. It's still in evolution, and it's the ideal experimentation software for MCUs. So have fun with Forth. And I say thanks to Chuck Moore, Brad Nelson, Dr. Ting, Peter Forth, all members of the FORTH2020 group, and all Forth lovers. That's it.
Wonderful, Christian. Nice work.
Thank you very much.
We are really out of time, guys. I will shorten my meeting as much as I can, and I will not show how to install ESP32 Forth. I will only show a couple of experiments. We need to be direct and go straight to the point. So I share my screen. And here what you see is the two windows. Probably you can see the video here on the left, and the terminal. I am on the terminal with ESP32 Forth. So you see words, and it will listen. It's a listing of all the words you have on the dictionary in the moment. And I created, I put in this board, this experimental board, you have the ESP32 Forth, the ESP32 chip, and you have the MOSFETs. I installed 3 MOSFETs to control for Christmas a light. And so I did a LED strip, and you can see it here with a test LED. I type and it starts running. You see the Christmas light. It's not a perfect well, I wanted to make a tree or something more like Christmas, but you see it's working. And this is controlled only by these 3 MOSFETs and directly from the outputs of the ESP32. You have here the output, and here is the cable, and it goes directly to the MOSFETs. I had no time to control the PWM of the MOSFETs. I will do this in the next meeting. But I had a problem with the hard disk, but I will show you how to control a servo motor here. I am waiting the demonstration, this test LED to stop. It will stop in a moment. And I also will show you the digital to analog output of the ESP32. I put this old multimeter to show you the analog output of the chip. So Christian explained it very well. We have this fantastic site with all guys helping us from the community. You see different projects from these ones are my projects. Then you have Atle's project. All the Forthmobile is here. The ultrasound, testing the board, everything is here. Atle did 2 sub menus, so you have all the information. On project 3, you have my Forthmobile. I will show you my the demonstration finished, so I can show you. Well, here I am back. For example, I have the OLED here attached, so I make a OLED in it. OLED, sorry, this is the vocabulary, OLED in it. And you see it's the OLED working here, running. In the future, I will add this MAX 7219. I wanted to have it finished for this presentation. It was not possible because of this accident with my hard disk. But you see now a demonstration of the servo motor. So I have the servo, RC servo. And if I want to move it to 90 degrees, I do 90 servo. And you see it goes to 90 to 45. I go to 10 servo. It goes to 10. And I do, for example, 3 servo test 2. This will start spinning the servo. Okay, and where are these words? These words you create. This was the question of Ronnie here. I have it on Messenger. Ronnie asked me about how you work with this. You create, Ronnie, you create your words here in a notepad. For example, I use Notepad. You see. And you copy this. There is sound. There is a, please tone down your volume. It's too noisy. I copy here, and the ESP32 Forth is running on the chip, so you don't need to compile nothing more. You simply send the words. So. And the interpreter is compiling in the dictionary the new definitions. So if I do, for example, green on will put the green light on. Here you see high to pin 14. Green off will put down low pin 14. So green on. And you see now the light is green. So I do green off and do red on. You see? And do red off and do blue on. Blue, let's mix, for example, red on with blue. So we have a almost orange, and then green on. and then we have almost a white light. And for example, RF, this is an abbreviation, BF, and GF. So this is forth. This is what forth. It's different to other languages. You don't need to compile. You simply talk to the chip, to the board, and if you have a Forthmobile like Atle, I will show you mine. This is my Forthmobile here. I have in the front an OLED here. I have a laser sensor. I have a compass. This is the compass. And this is a L298. This is the driver of the motors. And Atle has 4 motors. I have 2 motors only. And I have the gyroscope. This is the gyro. I have the battery sensor. And of course, the battery is here below on the. I don't know if you can see it. Batteries are here below the board. I don't have a board, a PCB board like Atle. I have only this experimental board, but I have another Forthmobile I will present. This is a simpler one. Let me see where it is. Here. This is a simpler Forthmobile, which does not need any drivers. It will talk directly to the RC servos. And these wheels are from Mayonnaise, a Mayonnaise lead. So it's very inexpensive, and the board can be made of wood. This board, this chassis can be made of wood or of plastic, out of plastic, of a strip of plastic, or any material, acrylic, and you only need a wheel, a spinning wheel in the back, and the 2 servos, and only 1 ESP32 on top. There is a way to make a very inexpensive board using Arduino Uno, and you cut the Arduino Uno in the middle, and you use the 2 halves of the board, and so you get a very inexpensive board. I am trying to make this kit as inexpensive as possible. For almost nothing, you can create and follow the FORTH2020 project of Atle and of us. And I was inspired to use these servos by the Dutch FIC members, which created a similar robot. I don't know if the name is Ushi, probably. If some of them is here, they can tell me. But it was the Ushi robot, I think.
Yeah, that was correct. Yeah.
Dutch FIC has a fantastic robotic group, and Willem and Albert Niethoff, no? They made this fantastic. Okay. I wanted to show the analog outputs, and then my demonstration is finished. Analog output is only to type DAC. For example, I do 100 to the DAC, and you see the multimeter. It's moving, and 0 to the DAC. it goes to 0, and test DAC, it will go up and down slowly. It's incrementing. It's a loop. It's incrementing the voltage and diminishing. Now it's going down. So there are so many possibilities with when you have a Forth installed in a chip like this. And another thing which is very important is the Wi-Fi, because I am now working with the cable, but when the Forthmobile is running in my room or outside of my house, I use Wi-Fi and I use a smartphone to control it. This is all developed by Dr. Ting and by Brad. So I took this original system, I implemented, and I was so happy to see with this simple interface and a simple chip, you can create so much experiments. Christian has shown you. There is no limit, and Atle, I dream with his presentation and with his code. He's fantastic. He did a fantastic job with the Forthmobile. I hope many more of you, probably Roy now in Bangladesh or is it okay, Bangladesh, are you, Ronnie?
Yes, sir. I am from Bangladesh.
Well, probably we can help you as a group or individually to make your next video with Forth, because you did a wonderful robot with a cake, and you can send a cake to Dr. Ting and another cake to Brad Nelson with your robot.
Sure, sir. I try to experiment with Forth code, and you already shown us. So it's a great pleasure to me to meet all of you. I'm really interested all about kind of Forth code. In this past day, I think the Arduino code is for Arduino, but there are lots of code like a Forth code. It's really awesome, sir.
There are many possibilities.
A helper.
Many.
Yes, sir. So I'm really communicate with genius, a teacher I get from you. Thank you so much, sir.
Ronnie, how many million people live in your country?
There are 20 million people are living in our country. And here lots of students try to learn how to robot work, but there's this situation.
You are officially named now in this moment. I name you officially the ambassador of the FORTH2020 group. Fine. Yeah. You are the ambassador for Bangladesh.
Thank you, sir.
And you, sir. We hope in the next meeting to have only 10%. I don't want everybody from Bangladesh, but only 10% learning Forth with us.
Yes, sir. It's really a pleasure to me. I'm only already I am working a daffodil group. They are working robotics, but but their country want to learn. Really interested people are there. So there are so many interested with robotics sector. So
I know.
This sir.
I will say another thing. Thank you for everything. We keep them later in the chat. Brad and Dr. Ting, I am doing a lot of effort to contact people in undeveloped countries. Like Brazil is developed, but not very much, and we have a lot of possibilities to use Forth.
Lots of equipment we get slowly. They're different from you and us. 20 or 1 month. So then we order something realistic and order something material kind of robotics, so there's lots of cost here. So that's why we are really back to with us.
From my experience, I see people in development countries, they have chance to buy boards of $50, $100, $200. It's no problem for them. But in undeveloped countries, $5, $7 is very expensive. And we need to make a very low cost projects for engineers and robotic students. And there are a lot of universities and there are a lot of students making wonderful things with very limited hardware. So I think this is the chance for Forth. Forth has a lot of chances in these countries, and in other countries, like in Germany, I speak very much with Ulrich about this. They have possibilities, students, to buy everything. So they can buy different, they have many alternatives, but in undeveloped countries, they don't have the chance. And with low resource, if you give them more power, they will appreciate that. They will see the difference of force and how to create robots with force. This is my idea.
Yes, sir. Thank you so much. I hope this is a good communication with all of you. I think all are help to us for develop our robotics sector, and especially Peter sir, you also thank you, sir.
Bye bye. Thank you.
Thank you, sir. So,
Pablo, ¿tú quieres mostrar el computador Forth para Guido? No sé si Guido está aún en el... Do you want to show the computer, the Forth computer, briefly?
Why, Peter? I dismantle.
Ah, okay. And then next time, Guido will come next time.
I show with this camera.
Ah, okay.
This is my SP34, 32. I cut the cable of old monitor and put in the protoboard and right. You have right, Peter. In some sense, not have make a computer with a microcontroller not have sense. But I am software people, no hardware, and I not work with hardware, and is the project I'm right. Here and
Look, Guido, for you. This is for you.
Guido make working in your house. I think perhaps I not make much documentation for making things and have unfinished work, but I forgot. Here with keyboard. I make a directory of the file system. I have a code log snake, and words. This is the dictionary. When see the presentation of Peter Shakaki, my version of Forth internally is very similar to Taichung Forth, but Peter work all in assembly, and I work in C. This is a game. And I have an editor. Right. This is all the form. The R3. And I don't remember when
we can make a new workshop of this SP32 and show again, and Pablo will show to Guido and probably out of the meeting, so people who don't are interested to participate, we talk hours of this, because it's so much so much information to pass to a beginner and to somebody who is starting with this. There is a lot of information.
Yes.
This is a fantastic work, Pablo. Fantastic.
Thank you, Peter. Thank you.
Well, who else wants to say something? Because I think we are over time again. No, Ulrich?
So a little bit, but it's interesting anyways. So that's rather good.
And it was a very nice meeting, end of year. And yes. I wish everybody to have a fantastic Christmas and end of year party also.
Mm-hmm.
We enjoyed very much.
Yeah. Time for
thank you so much for your efforts this year, Peter. This is a great group.
Yeah, thanks, Peter.
Thank you to you, Brad. You are the heart of the project, and Dr. Ting and everybody SVFIC. And we had the great pleasure of having Ulrich from German FIC and Klaus Kohl and all our friends from Germany. And well, this is a fantastic group of Forders and people from all of the world. Bill Ragsdale with his fantastic presentation. Guido from, I don't know how to pronounce, Turkey or Turkey?
That's Turkey. Türkei. Ich bin von Deutschland in die Türkei gezogen.
Türkei, for me, yes. It's besser für uns. Türkei. Matteo from Italy, Alexander from Spain, and I see Dimitri from UK, and Albert from Netherlands, and Camilo, Joe O'Connor, everyone in the meeting. Guys, I wish you all the best for seasons and keep fording.
Happy New Year, 2022.
Yeah, and we're doing great stuff in 2022. So
Feliz Año Nuevo. Happy New Year.
Looking forward to the next meeting in January.
Fantastic.
Bye.
So bye-bye.
Thank you. Thank you.
Bye-bye. Have a good time.
Bye-bye.